Thanks so much for organizing this summer school. It's an extraordinary effort, and it's a real pleasure to be involved, and I think a great service to the community to have all of this available for free online. It's really, I think, unique in a sense, and so very excited to be here talking about Bayesian deep learning, but also more broadly how we can think about building models that learn and generalize from first principles. And part of this will be the journey I kind of went through as a PhD student in reasoning about model construction and generalization. It feels, or at least it felt then, like different communities were prescribing very different things about how we should fundamentally think about model design. If you look at econometrics, for instance, there's a strong emphasis on parsimony and building models with a very small number of parameters that are interpretable, etc. Whereas in machine learning at the time, and I would say still now, there is often an emphasis on building huge models, kind of as big as a house, with a lot of flexibility. And really, it seems like the goal in building a new model was greater expressive power. And so a lot of my PhD at the beginning was spent trying to reconcile these two perspectives in a sense. How could it be both, that we want parsimony and simple models, yet we want really highly flexible models that are very expressive? And part of the resolution was that, as I came to see it, that generalization was at least a two-dimensional concept. It wasn't just to do with flexibility. It really had a lot to do with the combination of model flexibility and inductive biases, which are broadly the assumptions that we make that enable the model to have preferences for certain types of solutions a priori over others. And that's something we'll be discussing throughout the talk. And that the talk will have 4 different parts, and we'll go through some of the details of each of these. Some of the especially new content that will be in the talk will relate to an approach to representation learning that doesn't explicitly invoke neural nets, but it still has a deep learning flavor. I think as deep learning matures, we're starting to understand that it isn't just about neural networks. It's also about deep graphical models, about hierarchical structure, about a lot of the high-level ideas that sort of have provided deep neural networks with good inductive biases for generalization on a number of different problems. And so we'll touch on functional kernel learning. We'll also talk about other types of kernel learning, which are in a way how you do representation learning with Gaussian processes and other types of kernel machines. And we'll also talk about optimization procedures, which have been inspired by Bayesian deep learning in a sense. In many cases, it can be computationally burdensome to carry around a lot of models that we might want to be using if we're deploying a Bayesian neural network. And so one interesting research question is whether we could represent something like what we would get through a Bayesian model average with just a single model. And one way we can do that is through optimization. 1 second. Okay. And so in that context, we'll also be discussing loss landscapes and how we can try to understand the geometric properties of the objectives that we normally use to train neural networks in order to provide both better Bayesian approximations, but also just better solutions if we're ultimately going to be doing something like optimization, as well as better exploration of these loss surfaces if we're trying to use procedures, especially like stochastic gradient Markov chain Monte Carlo. And in a way, I would say, one distinguishing property of Bayesian procedures is we're really not trying to bet everything on a single solution. We're trying to consider all solutions and then take a posterior weighted model average. And that means that exploration, in a sense, is going to be particularly crucial. From the perspective of optimization, we just want to find the solution with the lowest loss. There are other properties that can affect generalization, like the flatness of the solution, etc. But fundamentally, the optimization problem is set up to find the lowest loss solution. Whereas from a Bayesian perspective, we want to move all over the surface. And so when we're thinking about stochastic gradient MCMC algorithms, we'll really care about things like learning rate schedules beyond just using them to try to find the low loss solution efficiently. Okay, so to start, we have this comic from XKCD, where we have 2 people talking. First one says, this neutrino detector measures whether the sun has gone nova. Next person says, then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it tells the truth. First person says, let's try. Detector has a sun gone nova. We hear the dice rolling. And then it says yes. And then the figure splits, where we have the frequentist statistician saying the probability of this result happening by chance is 1/36, 1/6 squared, which is less than 0.05. So I conclude that the sun has exploded with statistical significance. And then the Bayesian says, bet you $50 it hasn't. So this cartoon isn't a perfect description of the two camps in a sense, but you might say, well, if your reaction to this cartoon could depend also on what field you're coming from. If you're a game theorist, you probably would say, why just $50? Why not everything? Because if the sun has exploded, you have nothing more to lose. So in this sense, the Bayesian is also being a bit foolish. If you'd like to sort of see a detailed calculation of the posterior odds of these different hypotheses, which is something that Bayesian would want to compute, you can try Googling this, and people have gone into quite a bit of depth in trying to come up with a reasonable sort of ratio of odds, given that the detector is telling us that, yes, the sun has gone nova. The basic intuition, though, is that we've probably played a number of board games and rolled 2 6s. This isn't a particularly unusual occurrence. The sun exploding would be a priori an extraordinarily unlikely occurrence. And so that's really going to dominate when we compute the posterior odds of these two hypotheses. And there are a number of fun examples in David Mackay's information theory textbook, where he computes ratios of posterior odds for various different hypotheses, and also argues that from the Bayesian perspective, if we're doing model selection, the marginal likelihood, or the Bayesian evidence, is going to automatically favor a model of low complexity as long as it's consistent with our observations. So there's this fun example where we have basically a tree and what appears to be a block behind the tree. And then the question is posed, well, maybe if we had X-ray vision, we would see that it's not really one block, it's 2 blocks or 10 blocks or 100,000 blocks. But if we didn't have X-ray vision and you were just to ask someone how many blocks are behind the tree, they would almost certainly say with pretty high confidence 1 block, and they might try to rationalize that decision by saying it might be a remarkable coincidence for there to be 2 blocks of exactly the same height and color behind the tree, for instance. And so this is sort of an Occam's razor property that's actually automatically encoded in Bayesian inference. And we'll see some examples of that throughout the various parts of this tutorial. And so even if we don't have a prior that says that these 2 hypotheses are equally likely, we can have a posterior and a marginal likelihood, which will be favoring the simplest explanation that's consistent with our observations. And from an information theory perspective, this is also connected with what are called minimum description length principles, where we want to basically provide the most compressed representation of our data, and that will tend to capture a lot of regularities that will provide good generalization. Okay, so I'll start with a pattern recognition problem. You may have seen me ask this before if you've seen some of our recent talks, but it's a nice way of tying everything together. So we have our airline passenger numbers recorded monthly, and we'd like to make predictions, say, into the future up to 1961. And we'll consider 3 different modeling choices. Choice 1, a linear function. Choice 2, a cubic polynomial. And choice 3, a 10,000th order polynomial. So at this point, I'd like to pause and take a vote. And I think the summer school has a poll set up that you can answer, so that you can say which choice you might make for this particular problem. So I'm seeing a lot of 1s and 2s in the chat, no 3s. And 3 is precisely what I'm going to be arguing we should be doing throughout the tutorial. And in fact, I might find 3 unsatisfactory because it's not sufficiently flexible. So in practice, though many of us would indeed go with choices 1 or 2 for fear of overfitting, we know that there's some setting of parameters in choice 3, the WJs, which will provide a better description of reality than could possibly be managed by either choices 1 or 2, which are just special cases of choice 3. And if we had a good way of learning those coefficients, then we should expect better performance. And a good modeling procedure should try to capture our honest beliefs. And our honest beliefs are typically that the real world is a complicated place. Also, in practice, many of us, without really thinking about it too actively, are already using models with many more parameters than data points. We often use neural networks, big residual nets, for instance, that have tens of millions of parameters on problems like CFAR 10, which have 50,000 data points, and find that we get very good generalization. We're also seeing empirical results like double descent that suggest that we can get very good performance with a large number of parameters. And as we'll see in the last part of the talk, those results are entirely consistent with a Bayesian perspective, where we really don't want to be treating parameter counting as a proxy for complexity. And instead, we want to be using flexible models that also have reasonably good inductive biases. And in the next part of the talk, which we'll actually be doing today, we'll be considering models with an infinite number of parameters that are, in a sense, like if we could use an infinite order polynomial, and finding that we can get very good generalization on problems with even a very small number of data points. So throughout this tutorial, we'll really be arguing to build models that are as flexible as possible. And to start understanding the motivation for such models, it's helpful to be thinking from what's called the function space perspective, where we're not directly sort of parameter counting and considering the parameters, but rather considering how those parameters come together with a functional form of a model to induce a distribution over functions. So here we have choice 1, the linear function, W0 plus W1x, and we just put a standard normal distribution over these parameters. And this will induce a distribution over functions with different slopes and intercepts. And we can visualize this distribution by sampling from our prior over W0 and W1. We get different values, and then we just draw the corresponding straight line. The gray shade here shows our 95% credible set, which contains 95% of these functions. And the solid blue line shows our expectation of this distribution over functions. In this figure here, we have a conceptualization of all possible data sets on the horizontal axis, and the marginal likelihood, or the evidence that I was just referring to a few minutes ago, on the vertical axis, which is the probability that we would generate a data set if we were to randomly sample from the parameters of our model. And so in blue, we have a conceptualization of that linear model that we were just considering. No matter which W0s and W1s we sample from this distribution over the parameters, we won't be able to generate many different data sets, just straight lines with different slopes and intercepts. And because this marginal likelihood is a proper normalizable probability density, it's going to have to give a lot of mass to those data sets because it's not representing any other data set. On the other hand, we can consider a different type of model. For instance, maybe a really huge multi-layer perceptron and a broad distribution over the parameters, and such a model might be able to generate quite a wide range of data sets, but it could distribute its support over those data sets very thinly, such that it's not strongly preferring many data sets over many others. And so this type of model will be said to have not very good inductive biases, which describe which solutions we think are a priori likely. We can consider a third type of model, like a convolutional neural net, which is in fact very flexible, but it also has very strong inductive biases encoded through properties like translation equivariance, this idea that if we translate an image, its class label should be unchanged. And these inductive biases are very important for generalization on a lot of high-dimensional natural signals. And in fact, there are other types of symmetries that we might also want to capture. So this green model, in a sense, manages to do both. It manages to both be flexible, but at the same time have good inductive biases that'll also be important for good generalization performance. And throughout this tutorial, I'll argue that these are really the properties that we want. Large support, being able to represent a lot of different solutions a priori, because that's just representing our honest beliefs about the world, that it's a complicated place and we want to cast a wide net. At the same time, we don't necessarily think all of those solutions are likely. They might just be plausible, not probable. And so we can reflect that with inductive biases. And we should really be careful not to conflate flexibility, which I might call the support in this instance, with complexity. We can have really flexible models, like the models I briefly alluded to a few slides ago with infinitely many parameters, that in a sense are also quite simple. They have fairly simple inductive biases, which enable great generalization on problems with even a small number of points. And so in this figure on this slide, we have in the first panel what we observed on the last slide, plus 3 additional panels, which describe what happens as each of these models is exposed to a given data set. So the green model has large support and also reasonably good inductive biases, so that when it observes data, it's able to efficiently contract around a good description of reality. The second model in blue has very limited support, and it actually can't describe anything that's remotely like the ground truth description of our observations. And though it is quickly constrained by the data, it in a sense is erroneously constrained, and it just collapses down onto a not very good solution. And then in this third model, we've cast a big net so that we can capture the truth corresponding to some setting of our parameters, but we have our inductive biases very thinly spread over all sorts of different solutions. So the model isn't able to efficiently adapt with new information. And so it doesn't really contract very effectively around a good solution and still doesn't provide very good performance. So in this tutorial, we'll be thinking largely from a Bayesian perspective. Even if not everything we're doing is explicitly Bayesian, it'll be motivated by this perspective. And I would argue that the key distinguishing property of a Bayesian approach is what's called marginalization instead of optimization. So that is, consider all possible settings of parameters rather than just bet everything on a single setting of parameters, which is what we do typically when we're performing optimization. And so in this figure here, we can see some data points, and we can in fact see many different functions that might be consistent with those data points, and in a sense could be reasonable. If I said, well, is it this solid blue function that we believe, or one of these other curves? It would probably be hard to tell. And probability theory just says that we should combine all these solutions together, and it gives us the sum and product rules as a good mechanism for doing that. So I've long been interested in Bayesian machine learning. I became quite interested in Bayesian deep learning, ironically, after listening to a talk about optimization, which could be ironic given what I just said, in that Bayesian methods could potentially be described as trying to avoid optimization at all costs. The argument that was being made in this talk was that mini-batch SGD would provide solutions which would typically generalize better than full-batch gradient methods, because they would converge to flatter regions of the loss surfaces that we're using to train these models. For example, mean squared error or cross entropy if we're doing classification. In this figure, we have the loss in black. On the horizontal axis, we have a conceptualization of parameters. The testing loss is in dashed red. And we can see that a flat solution has pretty good testing loss, but a sharp solution has pretty bad testing loss after there's this horizontal shift between training and test loss surfaces. And we would typically expect this shift even if the train and test points come from exactly the same distribution, if we're evaluating the loss functions on some finite set of points. You could imagine, for instance, if you added or removed samples from your training set, you would really hope actually that you would update your parameters. So unless the model is entirely determined by that data set, we would expect a shift. And the shape of the loss surfaces are relatively similar, because we still believe that the training loss is not a horrible proxy for generalization. Now, for this argument to really mean something, the different parameters within this flat region would have to give rise to different functions. So, for example, when we were considering that linear function, the different W0s and W1s gave rise to quite different types of solutions. And otherwise, the flatness might not mean so much. We could achieve it trivially, for example, through reparameterization. So if that's the case, then this idea of doing Bayesian marginalization, also known as a Bayesian model average, is particularly compelling, because it means that there's going to be all these different parameter settings that actually give rise to different functions, which are all compelling explanations for the data. So in a sense, we're actually getting quite a rich ensemble of diverse models. And that's going to provide a very different answer than if we just bet everything on a single model. So although it has taken some time for Bayesian methods to be broadly deployed in deep learning, where they're perhaps more standard when we're using models like logistic regression right now, in fact, the benefits could be the most significant on these types of problems, where our law surface is telling us, actually, there are a lot of good solutions to this problem. And the result that we'll get by basically doing this marginalization procedure will then be quite different. And so there are many reasons to be excited about Bayesian methods in deep learning. As we've just discussed, neural nets can represent many complementary explanations for the data. We can get better uncertainty representation through representing what's called epistemic uncertainty, which is, for instance, uncertainty over our parameters, distributions over parameters. We'll talk about that in more detail later, which is crucial for decision making. If we want to make a decision, it's helpful not just to have a point prediction, but to have a whole distribution over what the predictions could be and how probable they are a posteriori. And you might argue that if your method is inconceivably going to have any effect on decision making, then it might not really have, a practical impact. So these methods are very important, I think, for deploying deep learning in the real world. But a perhaps less well understood benefit also is just better accuracy, better point predictions. If we are combining all these great complementary models together, we'll often see much better accuracy in our predictions. And this is also something that's starting to be realized. It has been very successful in the past. So as you may know, neural networks have been around for quite a while, and their popularity has come and gone in waves. And in the second wave of neural nets in the mid-90s, Radford Neal showed by developing Hamiltonian Monte Carlo approaches to inference that Bayesian neural nets could actually win all sorts of different competitions and solve a lot of interesting problems. His approaches wouldn't scale to modern architectures, but those results do tell us that there's some treasure buried in the direction of Bayesian deep learning, and we just need to build the right tools to extract that treasure as a community. And as we've already started to discuss, and as we'll discuss much further, neural nets become much less mysterious when viewed through the lens of probability theory and Bayesian inference. Things like double descent become actually quite natural. The idea of having many more parameters than data points is really not a problem if we're not treating parameter counting as a proxy for complexity and we're thinking in function space. The idea that neural nets can fit randomly labeled images also isn't problematic from this perspective, where we want our models to be flexible, but we also need them to have good inductive biases. Why not? Well, these methods can be computationally intractable. They can involve many different moving parts, but they don't really have to. And there's been a lot of great empirical progress in the last year where Bayesian neural nets have been providing often better practical performance than classical training without a lot of significant overhead. And we'll be discussing a number of these methods in part 3. So here we have a brief outline. In this first part, we'll be discussing foundations. We'll be doing an overview of some of the other parts of the tutorial. We'll be really emphasizing the importance of model averaging in deep learning in particular. We'll be talking about epistemic uncertainty, and we'll be exemplifying a lot of these ideas with examples. In the next part, we'll be considering largely a function space perspective of machine learning, where we talk about Gaussian processes, infinite neural net limits, how training a deep neural net is like kernel learning. We'll also discuss functional kernel learning and Bayesian non-parametric deep learning. And in part 3, we'll be considering a number of practical methods for Bayesian deep learning. And we'll also include in this discussion Bayesian generative models, which I think are a very exciting and up and coming sort of area of research for Bayesian methods in deep learning. And in the last part, we'll be talking about model construction and generalization, including deep ensembles, their connection with Bayesian marginalization, how we can build on those connections for the multi-swag procedure, tempering in relation to some work about what are called cold posteriors recently, prior specification, rethinking generalization, double descent, width depth trade-offs, and trying to view many problems around generalization and deep learning from a Bayesian perspective. Okay, so We'll start out from scratch, just forgetting everything we know about statistics and machine learning briefly. And we'll use this example to introduce a lot of notation that we'll use throughout the talk, and also to start really reasoning about model construction and generalization from first principles. And so imagine we'll have a training set of n targets. So these could be like our airline passenger numbers, indexed by our inputs, the x's. So in this case, the x's could be different times. And our goal is to predict our outputs y at some test inputs x star. For example, if we're given airline passenger numbers that we observe here, we might be interested in predicting the number of passengers in 1961. And so I'd like you to pause just for a minute and just kind of relying on high school math and nothing you've learned since then, think about what approach you might try on this particular problem. So if it were me in high school, I would start by thinking about the functional forms that I'm familiar with, like sines, cosines, exponentials, polynomials, etc. I would look at the data pretty carefully and try to create some combination of those elementary functions to describe the patterns that I see. The function that I get as a result would have some free parameters, and I would try to learn those parameters by specifying some error measure. For example, the difference between the squared, the square difference between the outputs of my function and the actual points that I observe expressed here in this equation. And then I would minimize this with respect to those parameters somehow. However, many of the design decisions there would be pretty arbitrary. For example, it's unclear that I should use squared error versus absolute error or some other type of error measure to train this model. We could alternatively follow a probabilistic approach where we assume that the points are drawn from some latent noise-free function, f of xw, which would be like my functional form that I was considering, plus, for instance, additive ID Gaussian noise with variance sigma squared. And we can use that observation model to create what's called a likelihood, the probability density for the data that we observe. And then we could maximize that likelihood with respect to our parameters, in this case, the parameters w of our functional form and sigma squared, our noise variance. However, if we take logs, for example, of this particular likelihood, we can see that the objective that we get will give us the same answer as just choosing squared distance. And so you might wonder, well, what's the point of doing all of this if we're just getting the same answer in this case? And there are a couple of reasons why this perspective here is preferable. So first of all, it's much easier and more intuitive to think about, for example, whether our data has Gaussian noise than whether we should use a squared error function just out of the blue. And in fact, if we make other design decisions, like we use heavy-tailed noise, like a Laplace distribution, maybe we think they're outliers, then we'll recover different types of error functions, like the absolute error function. Also, if we believe our model to some extent, we can get an estimate of the noise variance in the data, which is great. And so we can basically use this type of approach to interpret design decisions which otherwise would have been kind of ad hoc, and to come up with new design decisions which might be compelling for a given problem. However, remembering what we know about statistics, you're probably aware that either of those approaches can be prone to overfitting. And in fact, that's probably why most people went with option 1 or 2 in that beginning question. We can try to combat overfitting by doing what's called regularization, where we introduce some kind of complexity penalty, which says that we don't want to use very large weights. And we can calibrate the magnitude of that penalty with a hyperparameter like lambda here, which can be set, for example, through cross-validation. We could also get some kind of interpretation of this penalty by considering a log posterior, which is equal to a log likelihood plus a log prior, and the log prior would be, in this case, a bit like regularization. Not Bayesian, because still we're doing optimization, betting everything on one hypothesis. But this is all a bit ad hoc again. It's pretty unclear how we should be penalizing complexity. Whether we want large weights or small weights would entirely depend on the parameterization of the function that we're using. And if we had many such penalties, it could get very expensive to try to learn these lambda-like parameters. We'd end up with a cursive dimensionality. And we'd also have to make all sorts of design decisions in doing cross-validation, like which validation sets we want to use, et cetera. And there'd be all sorts of trade-offs. We could alternatively follow a Bayesian procedure. There's not much you really need to know to deploy a Bayesian procedure in your own work. We have Bayes' rule, which is often expressed as a posterior being proportional to a likelihood times a prior. The normalization constant here, the marginal likelihood, is what we were considering on that slide where we had all possible data sets on one axis, and the marginal likelihood on the vertical axis. We have the sum rule here, which says that the marginal distribution over x is equal to the sum of the joint distribution over x and y, summing over y. We also have the product rule. The joint distribution over x and y is equal to the product of the conditional distribution p of x given y times p of y, or the conditional distribution of p of y given x times p of x, and we can actually derive Bayes' rule from the product rule. And so there's not a lot you need to remember to use a Bayesian approach in your own work. So ultimately, what we're really trying to compute in many cases is this marginal predictive distribution. So y given the data, bold y, but not y given parameters. And the sum and product rules just tell us that that's the integral of y given the parameters times the posterior over the parameters given the data, integrating with respect to the parameters. So this is called marginalization because the parameters w appear on the right-hand side of this equation, but not the left-hand side. We've marginalized out w. This is also a Bayesian model average. So in words, what it's saying is, don't just use a single setting of parameters, use all possible settings of parameters weighted by their posterior probabilities. And so this isn't a controversial expression. It's just a direct consequence of the sum and product rules of probability. And it represents what's called epistemic uncertainty over which function f of xw fits the data. So epistemic uncertainty is reducible uncertainty with more information versus aleatoric uncertainty, which is irreducible, which in this context, this running example would be like the noise in the data. And so there are many different solutions that could be consistent, and we should represent them. We don't have complete certainty over which function corresponding to which setting of parameters is the right solution given a limited amount of information. And this will help us sidestep issues associated with overfitting, because we're not betting everything on one model. We're not really doing any fitting. We're just following the rules of probability and trying to honestly represent our beliefs in the modeling procedure. We can also view classical training from this perspective as a special case of Bayesian inference, where we use an approximate posterior, which is equal to a delta function, centered on the maximum likelihood or regularized maximum likelihood, the map setting of parameters. When we substitute in this expression for Q into our expression for P of W given data in equation 11, we see that we'll actually just recover the predictive distribution that we get when we do maximum likelihood. We'll get P of Y given those maximum likelihood setting of parameters. And so we can see here a couple important observations. One is that even if we have an approximate posterior, which is not a great description of the true posterior, it could still be a lot better than just using an approximate posterior that's a delta function, which could be even a much worse description. And so, for example, if we use something like a Gaussian approximate posterior in deep learning, it won't capture the multimodality that we typically see in these objectives, and it'll miss a lot of important structure that we, in principle, do want to capture. But it could still be providing us with a much better approximation to this integral than what we would be getting with just a delta function. And so we don't need to perfectly approximate this integral in order to at least provide great improvements over what everyone else is already doing when they're doing regularized classical training. We can also see that this Bayesian approach is going to be most different from a classical approach when the posterior is not very concentrated around a single setting of parameters, or when the conditional predictive distribution, P of y given W, is changing quite a lot for different settings of W where the posterior has mass. And so this is exactly going to be the case with neural networks. And this is when we're most going to want to deploy a Bayesian approach. So neural nets can represent many complementary explanations corresponding to different settings of their parameters W, and we know that these loss surfaces are crazy, and we'll actually see some fun visualizations of these loss surfaces later on. There's an important distinction between Bayesian model averaging and some types of model combination or ensembling. So the fundamental assumption in a Bayesian model average is that a single setting of parameters corresponding to a single hypothesis is the correct setting of parameters. And some approaches to model combination assume that we actually want to use a combination model as a ground truth description of reality. And so the model average here, even though it is combining together different hypotheses, it's because given limited information, we don't know which hypothesis is correct, but we believe that one of the hypotheses is correct. And so this will typically be safe if we actually have a pretty broad hypothesis space, which contains all sorts of different solutions to a given problem. And if we have good inductive biases, then the posterior will start to collapse around a good description of reality. If the actual ground truth is a combination of models, then we could see the model average actually performing worse as we get more data. So there's a fun tech report on this called Bayesian model averaging is not model combination. So we'll now consider two different examples. So I'd like you to suppose that we're flipping a biased coin with a probability lambda of landing tails. And I'd like you to consider these three questions. First, one, what is the likelihood of a set of data? So we've done n flips, and we've recorded which ones are tails and which ones are heads. What is the maximum likelihood solution for lambda? And three, suppose the first flip is tails. What is the probability that the next flip will be a tails using maximum likelihood? And you might want to substitute in some concrete numbers for n, say the number of flips. Let's let m be the number of tails. And maybe we'll consider n and m are 1, for instance. So just take a minute, and if you have some scrap paper or something like that, think about this problem. Think about specifying your observation model, writing down your likelihoods, and maximizing it with respect to this parameter that we want to learn in order to determine the bias of this coin that we're flipping. Okay, so we just have a bunch of binary outcomes, a bunch of Bernoulli variables. So our likelihood is just going to be, assuming that these are IID flips, is going to be lambda to the yi times 1 minus lambda to the 1 minus yi, taking the product over the number of flips that we do, and yi can take 1 if y is tails, 0 if y is heads. If we just care about the likelihood of getting m tails in n flips, and we don't care about ordering, etc., then we just have a binomial distribution as our likelihood. Again, n flips, m observed tails, lambda is the probability of getting tails. We can maximize this fairly easily with respect to lambda. So we could take logs of this expression, for instance, and take derivatives and set them equal to 0 and confirm that we have an optimum and show that the maximum likelihood solution is m over n, where m is the number of tails and n is the number of total flips. So I'd like to ask whether you believe this solution, and I believe a poll is set up. And if you do believe it, why do you believe it? If you don't believe it, why don't you believe it? It might be helpful to substitute in some concrete numbers for m and n. So if we imagine that we've just done a single flip and we observe tails, so m is 1 and n is 1, then we're predicting that there's a 100% chance the next flip is tails, which of course is not in line with our beliefs. There's basically no information. And so if we arrive at a prediction that we clearly don't believe, then it's probably because our modeling procedure is not honestly representing our beliefs. And we can do something better. So let's consider how to follow a Bayesian approach here. We could choose a prior, which has a functional form lambda to the alpha times 1 minus lambda to the beta. And if we do that, then the posterior will have the same functional form as the prior. This is called a conjugate prior. The beta distribution has this functional form. The gamma functions here are just for normalization. And we can analytically compute the moments of the beta distribution. Here we have visualizations of the beta prior corresponding to different settings of its parameters. We could use it as a uniform prior if we want. So we could just reflect the belief, I don't know what the bias of the coin is. And that'll, as we'll see, potentially give us quite a different answer than just doing maximum likelihood optimization. We could also represent our prior saying, for example, we think that there's probably close to a 50% bias such that it's an unbiased coin, but we're not, maybe it's not quite 50%. Whatever is an honest reflection of our beliefs. And there's quite a bit of flexibility with the beta distribution here. And so applying Bayes' theorem, we can find our posterior, which will be beta distributed with parameters m plus a and minus m plus b. And so we can actually view a and b, the parameters of the beta, as pseudo observations of the flips. And here we have our predictor, the posterior expectation over this parameter, m plus a over n plus a plus b. And I'd like to consider 3 different questions here. 1, what is the probability that the next flip is tails? 2, what happens in the limits of a and b? And 3, what happens in the limit of infinite data? So we can see that if we set m equals 1, n equals 1, and we have a uniform prior setting a equals 1, b equals 1, then we're not predicting that there's a 100% chance that the next flip is tails. And so that's very important already. It's nice as a sanity check to consider limits of different settings of these prior parameters. And so if, for example, a and b are very large, we see that the prior will dominate in our estimator. If we have a lot of data points, if n is very large, then m and n will be large compared to a and b, and we'll eventually recover the maximum likelihood solution, which is exactly what we want. As we get more and more data, eventually the posterior will just collapse onto the maximum likelihood solution. And we can discuss why that happens in more detail later. And I'd like to also have you very carefully consider this last question. It's quite crucial. So does the map estimate that we get by maximizing the log posterior with respect to lambda, which compartmentalizes into the log likelihood plus the log prior, with a uniform prior over lambda, give the same answer as Bayesian marginalization to find the probability that we're going to get tails on the next flip, given what we've observed so far with a uniform prior? So let's take a poll, 1 for yes, 2 for no. Okay, at least one person answered no, which is good. Yeah, so we get a very different answer, as we've seen, when we substitute m and n as 1 and say a and b as 1, giving us a uniform prior. And this is a really crucial distinction. We should absolutely not think of Bayesian methods as regularized optimization. Priors are not regularizers. It's a fundamentally different mechanism for breaching our predictions. Even if we say that we don't know what bias we have a priori, it's just uniform for any value between 0 and 1, we're going to be averaging over all sorts of different solutions to get a different answer than if we did optimization. And in this case, with optimization, we can see that prior would have no effect. It would just give us the maximum likelihood solution because it wouldn't depend on lambda. And so if you don't get anything else out of the tutorial, really understand this point. Bayesian methods are not regularized optimization. And the fundamental difference here is that we're not doing optimization, we're doing marginalization. A posterior weighted model average over different types of solutions. We'll consider one more example and then we'll go to break. So we'll go to break in about 5 minutes. So suppose we have observations y1 up to yn from an unknown density, p of y, and we want to estimate what that density could be. We'll start by specifying an observation model. For example, we could assume that the points are drawn from a mixture of 2 Gaussians, and our goal is to estimate the parameters of those Gaussians. The parameters in this case would be the means and the variances of the different components and the weights. We can use that observation model to create a likelihood, and then we can maximize that likelihood with respect to our parameters, the mu's and the sigmas. And let's just forget about the w's for now. So I'd like to ask you whether you can just look at this equation without taking derivatives or anything like that and see a setting of parameters which will provide very good likelihood. So if we set the mean, for instance, of the first component, mu1 equal to one of the data points y1, for that term in the product, the x will just disappear. We just get 1 for that, and we get this normalization constant, 1 over the square root of 2 pi sigma 1 squared. We can make sigma 1 very small, and then that term would blow up to infinity. And this other term would still be assigning density to all the different points, so we wouldn't be multiplying against zeros. And we've got infinite likelihood with a solution that we clearly don't believe. I was going to ask you if you believe it, but at the same time, we can probably assume you don't. We don't typically believe that our data are generated from point masses. And when we reach an unbelievable answer, it's typically because we haven't honestly represented our beliefs in the modeling procedure. We could introduce a regularizer, which would go to 0 faster than the likelihood goes to infinity for that pathological setting of parameters. But this could be a little bit ad hoc, and in a sense, we might be okay with including the point mass solution if it's one of an uncountably infinite number of solutions. And in fact, we can use very highly flexible models, even with an infinite mixture of Gaussians, following a Bayesian approach corresponding to Dirichlet process mixture models, which provide very good generalization, even with a small number of points, by doing this Bayesian model average. So to summarize, ultimately, we're often trying to compute this predictive distribution corresponding to our Bayesian model average. And in deep learning, the posterior is going to typically be quite diffuse, meaning that it assigns a fair bit of mass to quite a variety of different solutions, and those solutions are often providing complementary explanations to the problem, such that a Bayesian model average will give you quite a big difference, maybe relative to other model classes. Quite often, in practice, to estimate this integral, which isn't analytic, one uses what's called a simple Monte Carlo approximation, where we take samples from some approximate posterior, either found through deterministic methods like variational Bayes, where we introduce some convenience approximate posterior, like a Gaussian distribution, and we then estimate its parameters to minimize the distance between the true posterior and the approximate posterior, like the KL divergence. For a variational approach, we could see classical training as actually a special case of this. There's also the Laplace approximation, which we'll discuss later, expectation propagation, and many other approaches. Once we've got that approximate posterior, we'll take samples from it in the simple Monte Carlo procedure, and that will give us our approximate predictive distribution. We could also get approximate but asymptotically exact examples from a Markov chain Monte Carlo procedure, such as Metropolis Hastings, which is quite popular, Hamiltonian Monte Carlo, which includes gradient information, and was pursued quite successfully by Radford Neal in the mid-90s with Bayesian neural nets, and stochastic gradient MCMC methods, which are up and coming and quite exciting because they algorithmically resemble SGD in a lot of ways, which means they can be applied wherever we apply SGD, often with better results. And we'll be discussing those a little bit later on as well. And we'll also discuss later how we might want to avoid the simple Monte Carlo perspective in some cases. If we're told we can just query our predictive distribution at a small number of locations, which is really the honest truth in Bayesian deep learning. These architectures are massive with tens of millions of parameters at least in many cases, and so it's very expensive to do forward passes and store these models. Where would we want to best query our predictive distribution to get the best possible approximation of this integral? And the answer would rarely be, say, well, take a few exact posterior samples, because they could be redundant. This just would not be a good strategy. So if we attack this instead as an integration problem, we can often get much better answers. And we'll discuss how deep ensembles is actually heuristic for doing that, and we'll consider other approaches as well, which build on that connection for better marginalization. So in this part, we'll be talking about a function space perspective. We've already briefly alluded to this perspective in understanding this model selection question in thinking about support and inductive biases, and we'll go a lot more deeply in this direction, particularly considering GPs, infinite neural nets, what happens when we really pursue this philosophy to its extreme and build neural nets as large as possible. And we'll also consider connections between Gaussian processes and deep learning from the perspective of wanting to perform representation learning and kernel learning. And we'll build on those connections for an approach called functional kernel learning, which really pushes the function space perspective quite far towards trying to do representation learning. And then we'll consider Bayesian non-parametric approaches for deep learning. So the parameters in isolation are completely divorced from the statistical properties of a model. For example, when we were considering that statistics from scratch example, we said that whether or not we want large weights or small weights would entirely depend on the functional form of the model that we're using, its parameterization. Yet, in practice, we often focus almost all of our efforts thinking about these nuisance parameters and trying to learn these parameters and reasoning about these parameters, when really all we care about is how those parameters combine with the functional form of a model, f of xw, to induce a distribution over functions. So ideally, we just would like to perform inference directly in function space, and in a sense, cut out the sort of go-between that we have with these parameters, and think about exactly what we're interested in modeling. And so let's return to this example again briefly, where we have a distribution over linear functions induced by a distribution over parameters w0 and w1. Here, if we sample different settings of w0 and w1, we get different straight lines with different slopes and intercepts. We can visualize this induced distribution over parameters. We could also consider a much more general model class where we have an inner product of a vector of parameters w with a vector of basis functions. So if we wanted to consider a polynomial basis, the entries of this vector of basis functions phi would be 1x, x squared, x cubed, and so on. We could also have a Fourier basis. This is a fairly general model class, and we'll put a standard normal or a multivariate Gaussian distribution over the parameters w with mean zero for convenience and covariance matrix sigma w. And I'd like to pause for a minute and ask whether you can derive the moments of this induced distribution over functions. So In equation 38, we have the expectation of this random function, which is random because of the randomness from our parameters w. And we also have our covariance function, just going to the definition of covariance. So if you have some scratch paper, just take out your writing utensil and see if you can derive expressions for equations 38 and 39 under the model expressed by equations 36 and 37. So the mean function is fairly straightforward here. If we take the expectation of W transpose phi, as we said, all the randomness is coming from W, so we can pull phi out of that expectation. And the expectation of W, just by our definition in equation 41, is 0. And so we just get 0 as our mean function. We can grind through the algebra under the definition of covariance in equation 43 and show that our covariance function, that is the covariance between a pair of random variables given by our random function queried at a pair of arbitrary inputs, xi and xj, these could be times, spatial locations, images, whatever we like, is going to be the inner product of phi of xi with phi of xj under sigma w. So the next question is whether there are any other higher moments. And the answer to that question is no in this case, because we just have a sum of Gaussian random variables given by equation 40, and Gaussians are closed under addition. And so this distribution over functions is in fact entirely encapsulated by its first two moments, its mean function in equation 42 and its covariance function, also known as its kernel function in equation 45. This is an example of a Gaussian process. And in this case, we can actually do inference directly over functions instead of worrying about the parameters. Formally, a Gaussian process is defined as a collection of random variables, any finite number of which have a joint Gaussian distribution. We can use a Gaussian process to define distribution over functions. F of x is distributed as a GP with mean m of x and kernel kxx prime. Means that any collection of function values, f of x1 up to, say, f of xn, has a joint multivariate normal distribution with a mean vector mu and a covariance matrix k given by our mean function, little m, and our covariance kernel, or our covariance function, little k. So on the left panel here, I have sample functions from a Gaussian process prior. To create this figure, I chose a set of input points, x1 up to xn. I then created my multivariate normal distribution, first by creating my mean function, evaluating my, first creating mu, this mu vector, by evaluating my mean function at all of these input points. And in this case, my mean function I just chose to be 0. So that's just this solid blue curve here. And then creating my covariance matrix by evaluating my covariance function, or my kernel, at all possible pairs of those inputs. So I'll get some n by n matrix. And then I just sampled from that multivariate normal distribution, and I got the black dots, which are the random function values. And then I sampled from exactly that same distribution 2 more times, and I got the purple curve and the green curve. And here I've just joined the dots together. The gray shade shows my 95% credible set. 95% of these functions are contained within the shade. In the right panel, we've conditioned on some data denoted by crosses, and we've inferred a posterior over functions. And here I'm sampling from that posterior to get the black, purple, and green curves. The gray shade shows our 95% credible set. And the solid blue curve, in this case, shows our posterior mean function. So the expectation of this posterior distribution over functions given those observations given by the crosses. And this is, for example, what we might want to use for point predictions, and the credible set is something that gives us a sense of uncertainty. Very crucially, the statistical properties of these functions are very tightly controlled by our choice of covariance function, our choice of kernel. The kernel, in a sense, defines the support and inductive biases of our model. To create these figures so far, I've been using what's called the RBF kernel, the radial basis function kernel, also known as the Gaussian kernel or the squared exponential kernel. And it's equal to just a parameter squared, a squared, times the exponential of our negative Euclidean distance, normalized by, or not normalized by, divided by 2L squared, where L is what's called our length scale hyperparameter. And so this covariance function has a very intuitive inductive bias that random function values that are close together in the input space ought to be more correlated than function values that are far away in the input space. For example, airline passenger numbers under this model between 1951 and 1952 will be more correlated than between 1951 and 1961. So this is actually a pretty broadly applicable inductive bias, and the extent of these correlations will be determined by this length scale hyperparameter L. So if L is small, all the function values basically become uncorrelated. If L is large, then they're correlated over long distances. A is an amplitude parameter, so it controls, in a sense, the height of these functions. On average, the L controls the wiggliness of these functions. In the top right panel, we have a visualization of the entries of a covariance matrix constructed from an RBF kernel evaluated at all possible pairs of ordered 1D inputs, where we see this pronounced diagonal band, indeed saying that things that are closer together in the input space in terms of Euclidean distance are more correlated, higher covariance. As we move away, we actually get uncorrelated. So let's actually instantiate some values for these hyperparameters. Let's choose an A0 and L0 for our amplitude and length scale, and we'll observe some data and look at the prior and posterior over functions. And I'd like you to look at these figures and tell me if anything seems strange about these functions, and it could be actually a little bit subtle. So this is one of the polls. Feel free to respond to the polls. Yes, they look strange. 1, 2, no, they look perfect. So to me, they look a little bit too wiggly. They're oscillating pretty quickly. The length scale perhaps was a bit too small. We see the posterior mean sees a data point, and then it kind of shoots down to the prior mean, which is 0 in this case. So maybe we should consider a larger length scale like here. And they'll ask, does anything look strange about these functions? But to me, it looks like we overshot it. Like, before the other functions looked a bit too complex, too wiggly. These look too simple in a sense. They're too slowly varying, maybe over smoothing the data. So we can evaluate our marginal likelihoods. We can actually, in the case of regression here, analytically integrate away our Gaussian process and compute our evidence using the sum and product rules here. We have our likelihood times our prior in this case, integrating with respect to our whole Gaussian process function. And again, the marginal likelihood tells us the probability that we would generate a data set if we were to sample from our prior. And we can use the marginal likelihood to consider model selection. So there's actually quite a beautiful discussion of this in Mackay's textbook on information theory. It's also considered in the Rasmussen and Williams book on Gaussian processes for machine learning and some other works. Again, we've got all possible data sets on the horizontal axis. And on the vertical axis, we have the probability that we would generate each of those data sets, this density. And we can imagine if we have a very small length scale, everything's uncorrelated, so we just have white noise. So surely we've got flexibility. We can generate all sorts of different data sets, but everything we generate will be completely different than anything we've generated so far. And so we're just spreading our mass very thinly over these data sets. We're going to have very bad inductive biases. Whereas if we have L very large, as we saw, we almost start getting basically just straight lines again, even though we do actually have support for quite a few data sets. That support is very strongly concentrated around simple solutions. For a given data set, the marginal likelihood will automatically favor a model of appropriate complexity. It'll have this Occam's razor property. And in fact, if we optimize this marginal likelihood with respect to this one parameter, we get the fit in green, which does appear to intuitively have an appropriate level of complexity. And I'm sure if we were to do a poll, which of these three choices would you use, the red curve, the pink curve, or the green curve, most of us would go with the green curve for fitting this data. So we can see that we automatically sort of favor this nice minimum description length representation of our data and the marginal likelihood. So at the beginning of this part, I started by saying, well, we can consider some familiar weight space models and then derive the corresponding covariance function we might use for a Gaussian process and then deploy this model in function space. And then I said, well, let's just use the RBF kernel and see if we can get some intuitions. Now we'll step back again and actually derive that RBF kernel from first principles. So we'll again consider a model that's an inner product of a vector of weights and basis functions, but here we're just using scalar notation instead of vector notation. So we're just explicitly writing out the sum that corresponds to that inner product. We'll put a Gaussian distribution over the weights as so, and we'll consider radial basis function, radial basis functions for phi. You can sort of see where the RBF kernel is getting its name now, with centers ci, and we have this sort of bandwidth parameter L. Now, just following exactly the same derivation as before, we can write down what our kernel is. In this case, it's just given by equation 55. And we're visualizing this model in function space in this figure up here. And now let's see what happens as we take the limit of the number of basis functions to infinity. And so we'll want these basis functions to be dispersed across the whole real line. So let's make the endpoints log j and minus log j such that when we take j to infinity, we get infinity and minus infinity. We also want them to be densely dispersed. We want the distances between the basis functions to shrink to 0 as we take this limit. Here, if they're uniformly distributed, then the distances will be 2 log j over j, which we see goes to 0 as j goes to infinity. And this expression for the covariance function in equation 57 becomes a Riemann sum, an integral. We could have, for instance, chosen the endpoints to be root j and minus root j. I just wanted to make sure that the distances between the centers would shrink to 0. That wouldn't be the case if we'd chosen j and minus j, for instance. Okay, so we have this integral. We can substitute in our expression for the basis functions and actually analytically evaluate the integral and recover what's proportional to the RBF kernel. So I'd like you to pause for a moment and really absorb this result. It's really quite extraordinary. We've said here that we can use a model with an infinite number of parameters, an infinite number of basis functions, but using a finite amount of computation if we move to this dual representation in function space. This is actually called the kernel trick. And it's really quite extraordinary. I mean, in that first question I asked with the model selection on the airline passenger data set, you might have thought, well, even if we did accept we wanted to use a huge polynomial, if we take this philosophy to its extreme, how are we even going to represent these models in memory if we have like a 10 billionth order polynomial or something? And this essentially gives us the answer. It says, well, we can actually represent these models that have infinitely many parameters in this dual space and also have a lot of flexibility. So a GP with an RBF kernel is a universal approximator, and you can see this, you can see why intuitively from this derivation. If we were basically to shrink down all of these radial basis functions onto point masses, then we've got densely dispersed point masses across the real line that can take any height, so we can approximate essentially any function we want to arbitrary precision. And at the same time, we've seen that these models have very particular inductive biases. They generate functions in the prior that all have fairly particular statistical properties that will enable us to have good generalization, even on problems with a small number of points. So we have to be very careful not to parameter count as a proxy for complexity. And GPs with RBF kernels really give us a nice balance of large support and well-calibrated inductive biases. I'd like to make a brief aside at this point about the mean function of a Gaussian process. So in this talk so far, we've taken the mean function to be 0 for notational convenience. And this is also the case in many texts about Gaussian processes. It really is just for convenience. One can use any deterministic mean function without really changing the modeling procedure. In fact, it's quite standard to subtract off an empirical mean and then just use a 0 mean GP and then add it back on when you make predictions. Part of the reason for this is also because often the kernel is really the key object of interest in the exposition. And in practically, in many cases, there are degeneracies between the mean and the covariance function or the kernel, in which case it's therefore preferred to do the modeling in the kernel. For example, the kernel function shows up in this Occam's factor term that we get in the marginal likelihood as a log determinant, which we'll see later, but not the mean function. And so it's often preferable to really carefully consider modeling the kernel function and not necessarily do a lot with the mean function. Although at the same time, a mean function can be a great way of incorporating scientific inductive biases into a model. Sometimes there's this tension between using the physically interpretable parametric model with parameters that have some scientific significance that have been well motivated by theory, etc., or just throwing your data at a black box function approximator. In many cases, this is actually a false choice. In many cases, we can use both. We can use whatever model we would have used otherwise, the scientifically well-motivated parametric approach, as a mean function, for instance, of a Gaussian process, and then have like a non-parametric relaxation around it with the GP, which allows us to accommodate for the fact that no matter how well-motivated that approach is, it'll still be wrong in some sense. There'll still be some misspecification, and we can correct for that, and we can also represent uncertainty. And so really, you know, it's not, there's not a choice between using a Gaussian process and using some kind of alternative. In many cases, you can make that alternative your mean function and see better performance for doing so. Research on Gaussian processes in the machine learning community was instigated in many ways by work that Radford Neal was doing in the mid-90s on Bayesian neural nets, where he was really embracing this philosophy that we should build highly expressive, highly flexible models. And he took that to its limit. He said, well, let's build Bayesian neural nets that have an infinite number of hidden units. And when he took this limit, he actually showed that these models converge to Gaussian processes using a central limit theorem argument. And so we can see, just taking a simple neural net here, where we have our hidden units, H, hidden unit weights, U, hidden to output weights V, just a single output function f of x, a bias B, with fairly general assumptions. I mean, the U's don't even need to be Gaussian distributed, etc. We can use a central limit theorem argument and show that we'll get a Gaussian process. And as before, we can characterize that Gaussian process by its mean and covariance function, which we can derive in equations 65 to 67. And if we make particular design decisions, like we say that our hidden units are described by an error function, for instance, and we choose a Gaussian distribution for U, then we can derive an analytic expression for the kernel that we get in equation 69, sometimes called a neural network kernel. And we can look at what sample functions from a GP are like under that kernel function. We can see that they're qualitatively a bit different than the sample functions we were getting from a GP with an RBF kernel. For instance, they're non-stationary. We can see the behavior in the center here is quite a bit different than the behavior at the edges, whereas RBF kernels and many popular kernels indeed are stationary, meaning they're translation invariants. Although GPs under those kernels are highly flexible and can describe all sorts of different functions, the statistical properties of draws are kind of similar regardless of where you are in the input space. That's not true for this neural network kernel. We see it's non-stationary. So in the mid-90s, neural nets had been an active area of research contiguously for quite some time. And there was growing frustration over a lot of design decisions associated with these models, which activation functions, which hidden units, what optimization procedure, what learning rate schedule, how many hidden layers, how many hidden units, etc., and the lack of a principal framework to make these decisions. And since Gaussian processes could describe infinite neural nets, yet had these very simple inference procedures of the same 10 lines of code, you could get the same answer anywhere. They seemed like these maybe very compelling replacements. Like, let's just use these really nice interpretable models with a few design decisions and interpretable hyperparameters like length scale and a lot of flexibility, and forget about neural networks. And David Mackay did support Gaussian process research, but he was also a bit of a contrarian, and he wrote an article in an edited book about neural networks on Gaussian processes, where he has this quote: "How can Gaussian processes possibly replace neural networks? Have we thrown the baby out with the bathwater. And what he meant was that neural nets, when they were originally proposed, were envisaged as a step towards intelligent agents, which could discover interesting hidden representations in data, whereas Gaussian processes, at least with kernel functions, which were popular at the time, were basically just smoothing devices, even though they had all of these nice statistical properties. And so we asked, have we thrown the baby out with the bathwater in treating GPs as potential replacements for neural nets? The answer to this question is to build more interesting kernel functions which can discover interesting hidden representations of the data. There's nothing that you can do with a neural net that you can't do with a Gaussian process. You just need the right kernel. And so there's an approach called deep kernel learning, which combines the inductive biases of deep architectures with the non-parametric flexibility of Gaussian processes. These two things are really complementary, even though kernel methods and neural nets are often talked about, especially historically, as competing approaches. They're in many ways offering very different types of advantages, which can be naturally combined. Kernel methods can be seen as providing a very elegant way of representing models with an infinite number of parameters using a finite amount of computation through the kernel trick. So they give you an infinite number of basis functions. Whereas neural nets, on the other hand, give you highly adaptive basis functions with inductive biases that are well suited to a broad range of application domains. And so with deep kernel learning, we can get infinitely many highly adaptive basis functions structured by neural architectures, and we can learn the properties of those basis functions through a GP marginal likelihood. So that's a very different objective than how we would normally train a neural network model. And so we can use these deep kernel learning models for representation learning. Here we have the Olivetti faces problem, where we have faces with different orientation angles. It's a regression problem where we want to predict the continuous orientation angle of a new face. And we can see that when we project what the model has learned into 2 dimensions, where each face corresponds to a line segment and the slope of that line segment corresponds to the orientation angle of the face, we can see that the model is discovering a representation for the data such that faces with similar orientation angles are clustered together. So this is really non-Euclidean metric learning. We can also see this when we evaluate the entries of these deep kernel matrices in the left 2 panels, ordering the faces by orientation angles. Here we see a pronounced diagonal band, which shows that the model has learned that faces with similar orientation angles have higher covariance. This is not something that we could learn with classical kernels or covariance functions, which are based more on a notion of Euclidean distance. In the far right panel, we evaluate a learned RBF kernel on this problem, and we can see that its entries are quite diffuse. So from this perspective, in many ways, training a neural network is exactly like learning a kernel. It's learning a non-Euclidean similarity metric for our data instances. And we can capture this with Gaussian processes using the right kernel learning approaches. And one particular advantage of a Gaussian process is the ability to express a principal probabilistic objective for kernel learning, which might otherwise be difficult. So we can learn kernels with millions of parameters using this marginal likelihood objective and avoid procedures like cross-validation, etc. In this example, we have discontinuous data given by a step function. And we've got fits using a GP with an RBF kernel in blue, a GP with a spectral mixture kernel, which we'll describe briefly in red, and a GP with a deep kernel in green. The shade here in each case shows the 95% credible set. So from the perspective of a GP with an RBF kernel, even though we have a hyper-flexible model, the step function kind of data is such an unlikely draw from that model. If we can estimate noise, it's much easier for the model to say, well, actually, we think that this data is just noise because our inductive biases are so strongly opposed to this data being anything else. And so we'll just have a huge estimate for uncertainty and have a simple mean fit, which is what we see happens here. In red, we see that the spectral mixture kernel is able to provide a better fit, but it's still sort of over smooths. In green, we can see that the deep kernel captures this data quite effectively. And so there's a bit of a false narrative that GPs can really, over smooth data, have trouble with discontinuities and so on. That's not true. It depends on the covariance function that you're using. And with the deep kernel, you can capture sharp discontinuities and get nice predictive distributions. And you also have this sense of distance in the feature space, which is quite important. So there's been some work recently on single model Bayesian neural nets that sort of, in a sense, have these sort of distance measures encoded within them. And this is something that we get through deep kernel learning. And so that's actually very useful for capturing epistemic uncertainty. Here we consider an autonomous driving problem where we're trying to predict lane boundary positions, and we need to make decisions. And so predictive distributions are going to be very important for making decisions. We don't just want to know where a lane boundary is. We need to know the error bars to make a good decision. And so we use Gaussian processes with LSTM structured kernels and find that we get quite accurate point predictions compared to the standard LSTM models, as well as good predictive distributions. There are many other approaches we can use to develop kernels for representation learning, many of which actually don't rely on neural nets. And this is where this idea that deep learning isn't just about neural nets comes into play here. So this will be a bit advanced. Don't worry if you don't follow everything for the next few slides, but it could be of interest here. So I mentioned that many popular kernels are stationary. And there's a theorem called Bochner's theorem that relates stationary kernels to what are called spectral densities. They're just Fourier duals of one another. And so that means that we can reduce kernel estimation in many cases to spectral density estimation. Here we've just represented the two arguments of the stationary kernel as tau being x minus x prime, since these kernels are translation invariant. And so that means that if we attack this as a density estimation problem and say, well, mixtures of Gaussians are dense in the set of distributions, so we should be able to approximate any stationary kernel with a mixture of Gaussians in the frequency space, we can derive basically a closed form basis for all stationary covariance functions. And we can then just estimate parameters in this basis, the sigmas, the variances of the Gaussians in the spectral space, and the mu's, the means of the Gaussians in the spectral space, to do that kernel learning. And we can use our marginal likelihood as our objective, for instance, to learn those types of parameters. And so this is called a spectral mixture kernel. And this is just a brief recap of how we would often use such a model. So we might be considering regression. And our observation model is that we have our latent noise-free function given by our Gaussian process, plus, say, additive Gaussian noise. And that noise-free function could have a spectral mixture kernel with some parameters theta that we're trying to learn. So we'll learn that by optimizing the marginal likelihood, which in this case has the form of equation 75. So we have to solve this linear system and compute this log determinant. And once we have those parameters, we could condition on them and make our predictions. Of course, if we want it to be fully Bayesian, we still ought to marginalize these parameters as well. Okay, so let's return to the airline passenger number example. Here we've just joined the observations together into a curve. And let's consider various different possible fits and whether we believe them to be reasonable or not. So if we have this red curve here, would you think that this is a reasonable description of the data? No, almost certainly not. That's what we get from a GP with an RBF kernel. We see that it's kind of just smoothing this, in this case, quite a lot and reverting to a prior mean. Does this seem like a reasonable fit? I would say probably yes. And that's what we get through a spectral mixture kernel. And so this again shows the importance of representation learning in order to provide a long-range extrapolation. You may have noticed when I first asked this question about the airline passenger example in part 1, I said, consider trying to make predictions far away from the data. And part of the motivation behind phrasing the question in that way was that when we do extrapolation, we really expose the prior assumptions of our model. They become very, very clear. And we also really need to be able to do representation learning in these settings. So we can apply the spectral mixture kernel to a number of other types of extrapolation problems. Here, green is the withheld test data, blue is the training data. shade is our 95% credible set using a GP with a spectral mixture kernel. The other colors are extrapolations provided using GPs with other popular covariance functions or kernels. In the right panel, we're also visualizing the spectral density. So we said that a spectral mixture kernel was derived by using a mixture of Gaussians in frequency space. And so we can compare that to things like the empirical spectrum and the spectrum associated with things like RBF kernels. In this example, we're trying to recover an unknown ground truth kernel. So we have a controlled experiment where we generate data with a ground truth kernel in green. In the left panel, a heavy-tailed kernel. In the right panel, this quasi-periodic kernel. And then we just feed those data points into our marginal likelihood and then learn the parameters of the spectral mixture kernel and draw what we get. And we can see that it provides a pretty good fit in this instance. In red and purple, we see what we get using, respectively, RBF kernel fits and the empirical spectrum, which is related to just the Fourier transform of the data squared. So we can see that it's actually quite noisy. And this is because it doesn't have great inductive biases. It's not, for example, assuming that covariances are probably decreasing with distance, which is, in general, not a bad inductive bias. Here we have an autoregressive data set, which is representative, for example, of natural sounds. And it, in fact, has a negative covariance function which takes negative values. So the examples we've seen so far of Gaussian processes are continuous. This is a discrete valued Gaussian process, and we can drive its covariance function. And here with the spectral mixture kernel, we can actually capture negative covariances, which is interesting, and something that we think we probably ought to be able to capture in many cases. In many cases, for example, data have long-range negative covariances. A straight line fit would be one example. We also have this sync function pattern where we're basically observing the data in the top left panel and we're trying to fill in the missing part. We actually had a fun paper called The Human Kernel, which literally asks people to do extrapolations on these problems and tries to reverse engineer their kernel in being able to do this pattern recognition problem. We see that the GP, the spectral mixture kernel, can provide a good extrapolation in this case, although the extrapolations from GPs with other kernels aren't necessarily unreasonable there. Okay, so here we have airline passenger numbers. Again, we see the extrapolation again is reasonable, and this is all kind of automatic. The spectral density in this case is also kind of interesting. We can see that there are peaks in the learned spectral mixture spectrum that do correspond with what we get when we take the Fourier transform, but the Fourier transform is pretty noisy, and so this could be a replacement for a lot of these things. All right, so far I've argued that we, in many cases, want to follow a Bayesian approach because marginalization can be quite compelling and a good way of representing what's called epistemic uncertainty. And also that we want to, in general, follow a function space approach to modeling. And so taking this perspective further, we really ought to approach kernel learning from a function space Bayesian perspective, just the way we approach data modeling with GPs from a function space Bayesian perspective. In a sense, it's a bit strange that with GPs, we put all of this effort into deploying this Bayesian non-parametric distribution over functions to model observed data points. But then the most crucial aspect of this model, the kernel, is either very simply specified, yet we believe it probably to be quite complex to be a good description of reality, and doesn't necessarily capture representation of uncertainty and isn't really thought about from the function space. So the idea here with functional kernel learning is just to take this philosophy a step further in the hierarchy of our hierarchical model and say, well, let's also have a function space distribution over kernels. And we can sample prior kernels from this distribution. We observe some data. Then we can infer a posterior distribution over kernels, which should start to contract around something. And when we form our predictive distribution, we can actually marginalize away this whole posterior distribution over kernels. In this case, we'll actually get a non-Gaussian process. And so this is the hierarchical model specification, and the way that we do it in this case is to put basically a transformed Gaussian process over the spectral density, and then compute sort of this integral in order to evaluate our kernel function in data space. And we can see here we have draws of prior kernels, and then we have function draws corresponding to each of those kernels in this hierarchical model. And so this is at the top of the hierarchy. We sample these parameters, then we sample this GP, then we transform the GP, then we sample another GP conditioned on the kernel that we got as a sample from that step up in the hierarchy. And the nice thing about this is we can then intuitively control things like our mean function over kernels. Let's say we would have otherwise used an RBF kernel or a spectral mixture kernel or something else. We could say, well, let's just make that the mean function of our distribution over kernels, and that will concentrate our inductive biases in some nice way, but also allow us to do this interesting representation learning. And when we deploy this model on various different problems, we again see this automatic extrapolation. And we can also apply it to large-scale textures, for example, and see that we can extrapolate somewhat these textures, whereas with an RBF kernel, again, we kind of quickly revert to a prior mean. We also can consider multitask regression problems, and this is quite interesting in the context of kernel learning because often different tasks can be viewed as multiple draws from some shared generative procedure, in which case we get a lot of signal for doing fairly ambitious kernel learning. And here we consider precipitation, extrapolation in a bunch of different geographic regions where we're really sharing strength across these regions to learn a really flexible distribution over kernels and make quite good predictions as well as have good credible sets. Now, a big challenge in using Gaussian processes historically has been scalability. As you briefly saw in that set of equations where we were thinking about kernel learning, we need to solve a linear system and compute a log determinant over an n by n matrix if we have n data points. Now, a lot of the progress in deep learning has been driven not purely through methodological innovation, but also through embracing advances in hardware and in systems. We have packages like PyTorch, for example, which leverage auto differentiation and GPU acceleration very effectively. With GPyTorch, this fairly big project we have going, we try to find motivation and inspiration from that trajectory in order to really scale Gaussian processes through systems and hardware acceleration. So we build Krylov subspace methods that enable a lot of GPU parallelization, which in turn enables even exact Gaussian processes to run on millions of points in minutes. This is really quite a big step up from exact Gaussian processes on thousands of points, which has historically been a limitation. And we see that when we do that, when we use these exact methods, we see a big benefit to the non-parametric representation corresponding to these kernels that have infinite basis expansions, such that as we increasingly see more data, we are still very significantly improving in accuracy. Whereas most approaches to scaling Gaussian processes essentially turn GPs from a non-parametric model into a parametric model through a low-rank kernel matrix approximation. This would describe random feature expansions, inducing point methods, etc. And that means that these models won't necessarily benefit from large data sets. So for the first time, we can actually see how well exact GPs can do on huge data sets. And it's often representing a fairly significant gap with the approximate procedures. We can also introduce approximations which exploit algebraic structure in models that is basically a manifestation of the inductive biases that we'll need for good generalization. And so one way to do that is through an approach called structured kernel interpolation, where we basically start with a kernel matrix evaluated on a set of points U, sometimes called inducing points or interpolation points. Then we interpolate on that matrix to approximate the cross covariances between our inputs X and our inducing points U. If we did local interpolation, where we're just considering, say, the two closest points to the X that we're trying to consider in U space, then our matrix W will have only 2 non-zero entries per row. It'll be very sparse. And we can choose the points U in conjunction with whatever kernel we're using to create a structured matrix, which will also admit fast matrix multiplies. And then we can combine with these Krylov subspace methods like preconditioned linear conjugate gradients to efficiently solve linear systems. And so this gives us linear time complexity instead of cubic time complexity associated with Cholesky decompositions and log determinants and things like that. And importantly, it also separates additively across the number of inducing points u, m, and the number of training points n. So often we see something like m squared n sort of inference and inducing point methods. Here we have more like n plus m. And so that means we can make m really large and get a very accurate approximation. In fact, the approximation will be exact as we make m sort of go to infinity, and it'll converge pretty quickly for a number of interpolation strategies. Jake Gardner, one of my collaborators on GPyTorch, made this nice visualization of this structured kernel interpolation, also sometimes known as KISS-GP procedure, where we have these sparse matrices. We're considering a vector multiplication. And we basically are looking at the time and storage associated with each step. Now we have a structured matrix, in this case a Toeplitz matrix, times a vector v, which we can compute in m log m time. And then we have this product here. And overall, we've got very scalable inference asymptotically. And so the nice thing about this approach is we can just make m very large very cheaply. And so even though for a given m, maybe the approach wouldn't be as accurate as some competing approaches, without very much computational overhead, we can make m huge such that if we're considering instead accuracy versus runtime trade-offs, this method can be very compelling compared to the standard alternatives. There are a variety of other Gaussian process libraries like GPFlow, in TensorFlow, GPy in Python, BowTorch, which considers Bayesian optimization, A/B testing. This is what we often use if we're trying to do AutoML, hyperparameter tuning, experimental design, and so on. And these packages have different algorithmic foundations and use cases. There's been a lot of work on combining Gaussian processes with neural nets in various ways. So there's, for example, Gaussian process regression networks and deep Gaussian processes, which build hierarchical models replacing neurons in neural nets with GPs. There are many works that have extended Radford-Niels limits to multi-layer nets and other architectures. This line of work is very connected to neural tangent kernels for infinite neural net limits with promising results. Deep kernel learning, deep GPs, Gaussian process regression networks, and some other approaches are trying to sort of do metric learning in some sense. I think an interesting direction for a lot of these infinite limits corresponding to various kernels, like neural tangent kernels, would be doing some kind of kernel learning. We emphasize that when we're training a neural net, we're basically learning a kernel. And so in many cases, the kernels we get from these limits are fixed. And I think this is actually a very exciting direction for future work, thinking about how to do representation learning, kernel learning, and those kinds of frameworks. Also, as we've been seeing throughout this part of the tutorial, there are many ways to realize Bayesian principles in deep learning, in addition to the standard approach of marginalizing distributions over parameters in irregular neural nets. We've been considering how we can basically do Bayesian non-parametric deep learning through approaches like deep kernel learning. And I think in general, combining the principles of Bayesian non-parametrics, wanting an infinite number of parameters, wanting a huge amount of support, and so on, with deep learning is a really exciting area for future work and is an important part of the basically the activity in the Bayesian deep learning community. All right, that's the end of part 2. In the last part, we discussed foundational concepts around model construction and generalization, and how Bayesian model averaging and the representation of epistemic uncertainty is particularly crucial and interesting in deep learning. And then we started to discuss in more detail the function space perspective of modeling, including Gaussian processes, which allow us to directly model in function space, which is very nice, as well as what happens when we take infinite limits of Bayesian neural nets and derive Gaussian processes with various kernel functions, as well as a Bayesian non-parametric perspective of deep learning. Just for a little bit of organizational structure, the next 2 parts will take up about 35 to 40 minutes each, and then we'll have about a 30-minute fireside chat at the end of this presentation, where you can ask me any questions, as well as there'll be a discussion that's about aspects of my trajectory and what I was thinking about in my PhD and things like this, and sort of how I developed as a student. So as a brief recap, at the end of the last presentation, we were talking about a model or an approach called deep kernel learning. which combines the inductive biases of deep learning architectures with many of the nice properties of Gaussian processes, such as a non-parametric representation. So that's something that you could never get through a standalone neural net. No matter how big you build the neural net, it's not going to have an infinite number of parameters. And if you make the neural net really, really big, then it might actually be it might be difficult to control many of its statistical properties, which are fairly easily controllable if we're working within a Gaussian process framework. And so the basic idea behind deep kernel learning is you have a neural network transformation of your inputs, and then you have a Gaussian process applied to that transformation. The whole transformation is learned jointly through a Gaussian process marginal likelihood. We could describe this as an example of a last layer GP model where we start with a base kernel, could be an RBF kernel or a spectral mixture kernel, for instance, and then we transform the inputs with some nonlinear function g given by a neural network, typically that has its own parameters w, and then the resulting kernel is a deep kernel with parameters that come from the transformation g, as well as whatever parameters we started with in our base kernel. And actually, it's quite interesting to separately try to understand the properties of each of these types of hyperparameters. The base kernel hyperparameters will often give us, for example, length scales, which tell us how quickly we expect our function to be varying, at least in the feature space provided by the neural network. And in many of these papers, we try to interpret, essentially, what each part is contributing. And so in many cases, we do see better performance than a standalone deep neural network, but we also see some added amount of interpretability. The choice of which base kernel to use is also quite interesting. In the original deep kernel learning paper, we considered largely RBF and spectral mixture base kernels, but there are a variety of other possibilities, and I think an interesting direction for future work will be in considering new types of base kernels and how they might interact with what we're getting through the neural network transformation. Okay, so in this next part, we'll be considering a number of practical approaches for Bayesian deep learning. Here, where Bayesian deep learning is being largely construed as starting with some kind of neural architecture, like a deep residual network, and wanting to marginalize some kind of distribution over parameters in that network. And as I mentioned at the beginning of my presentation yesterday, a lot of what motivated my interest in Bayesian deep learning was the observation that when we're optimizing these networks, finding flatter solutions will often lead to better generalization. And in a sense, this seemed like actually a good argument for following a Bayesian approach, because if it were true, that means that there are these big regions of the loss landscape that contain a variety of parameter settings that all have low loss, but are providing complementary explanations to our problem, in which case just choosing one of them seems a bit arbitrary. We know that there's this loss landscape, it has all these good solutions, it's not only multimodal, but it has loads of sort of loss valleys containing many different global optima. And from that perspective, it seems kind of arbitrary to say, well, let's just bet everything on one of those. Like, you know, how do we know which one to choose if we're going to do that, for instance? And so if we're following a Bayesian approach, we're essentially integrating under a flipped version of this curve here. And this also means that the properties like flat solutions corresponding to better generalization will be automatically accounted for in some sense, because most of the mass of that integral will actually be contained within the flat regions rather than the sharp regions. So that's nice, because if we were to follow the sort of optimization line of work in trying to leverage this observation for better performance, we would have to start thinking about very rigorously how we would want to define flatness, for instance, and how much we wanted to favor it, and so on. And so we end up with this sort of rabbit hole that's kind of similar to what I described if we're considering procedures like regularization. Like, how do we define complexity? How do we want to penalize it? Is it going to be invariant to model architecture, etc.? And so, you know, these are all really hard problems, and we don't really need to worry about them if we're integrating. A lot of this will just be happening under the hood. And this is largely because we're not trying to bet everything on one hypothesis. We're doing this marginalization procedure, which is a direct consequence of the sum and product rules of probability. So what this does mean, though, is that in order to realize the benefits of Bayesian marginalization to a large extent, we're going to want to have a good understanding of the structure of these loss landscapes that we're navigating and training these neural nets, because we want to create good approximate posteriors. We want to figure out how to do this integral as effectively as possible. So the study of these loss landscapes is not just of interest in optimization, it's of extraordinary interest when we're trying to follow a Bayesian approach to deep learning. And in fact, I might argue that it's even more crucial, because when we're following a Bayesian approach, we're not ultimately just trying to find a low loss solution. We're really trying to navigate across this landscape continuously. So recall that the Bayesian model average that we often want to be computing can be expressed as in equation 3 here, where we have an integral of our conditional predictive distribution multiplied by our posterior. And as I've been saying, the posterior for neural nets, which has a direct relationship with the loss in many cases. The loss is often defined as a negative log posterior, is very complex, very multimodal, contains many complementary explanations. And this is why the Bayesian model average is particularly significant in deep learning, but it's also why we really need to understand the structure of these loss landscapes. So towards that end, early on, we discovered that if you retrain a neural network with different random initializations and converge to different basins of attraction, you can actually find paths which connect those solutions together in a subspace, such that you can walk along these paths and not really increase the loss along the way, and arrive at the other solution. And the way that you can discover these paths is to introduce a parametrized curve, like a polygonal chain or a quadratic Bezier curve, which has as its endpoints these two weight vectors that we found by running SGD twice independently, and then minimizing the loss uniformly in expectation over the curve in order to learn the parameters of the curves. That would be like the turning point that we use in some subspace. And so this looks like, for instance, a line integral of cross entropy loss, if we're doing classification, normalized by arc length. And we found that you could always discover these paths as long as you had at least a polygonal chain with a single turn. This was somewhat of a surprising result, because if you take a direct linear path between any two of these solutions, you incur pretty extraordinarily high loss along the way. You often have almost 100% training error if you try to take a straight line path between any two solutions. But if you do a polygonal chain or something a bit fancier, you can always find a subspace along which these modes are connected. And so this visualization here is actually a two-dimensional slice through a really high-dimensional loss surface. So we might have a neural network that has tens of millions of parameters. In this case, we are considering a large residual network. And we're visualizing the loss associated with that model by considering a plane where each point is an affine composition of 3 different weight vectors. And the height here is the value of the loss evaluated at each of those points. And so here we see a subspace along which these 2 different solutions are connected. Here we have a few other visualizations. We can see, even in these 2-dimensional slices, how extraordinarily sophisticated these loss landscapes are, and how difficult we can imagine they would be to navigate effectively. There are so many different local optima, and from this perspective, it seems especially arbitrary just to bet everything on one of them. Now, another interesting thing we found here was that these different solutions weren't only connected, but that as we were walking from one solution to the other, the different points in weight space were giving rise to models which actually provided quite different functions. And so there was a lot of functional heterogeneity along these paths. And so you could actually see this discovery, in a sense, as an empirical realization of that conceptual diagram we started with that was trying to motivate the idea that flat optima would generalize better. We are, in fact, seeing that there are these big regions of the loss surface along which we have very low loss, yet a variety of different parameters corresponding to a variety of different complementary functions that can describe our data. And so these regions actually exist. And also from this perspective, one might say that referring to whatever we discover by doing SGD optimization as a local optima is somewhat of a misnomer. We know that there's some direction along which the loss landscape is extraordinarily flat. And so the next question is whether we can directly leverage this observation in order to do more accurate and more scalable Bayesian model averaging. Can we actually recycle, for example, geometric information that we're already getting through regular SGD training to do a scalable Bayesian model average or a scalable posterior approximation? So the first step in this direction was actually to derive an optimization procedure which would provide better generalization. The idea is that we would start at a standard sort of learning rate, and then we would decay as usual, but we would actually decay to a relatively high constant learning rate or a cyclical learning rate. And the reasoning here is that normally when we run SGD, we actually converge to the periphery of a set of low-loss solutions. And the reason for that is because there's no real motivation for this gradient descent procedure to move deeply inside this region, because all these points have similar values of the loss. There's no gradient signal. And so what we do here is we increase the learning rate such that we're kind of spinning around this set of low-loss solutions, this loss valley. And then what we do is we take an equal average, and this is very crucial, an equal average, not an exponentially moving average, of these solutions in order to find a centered region in this loss valley. And so this procedure is called stochastic weight averaging. And as of today, it's now natively supported in the new version of PyTorch, PyTorch 1.6. And so it's just as easy to use as SGD or Atom or whatever else. And in fact, can be applied pretty effectively to pre-trained models. So if you've already trained your model with SGD, Atom, or really anything else, you can just increase the learning rate and apply this procedure for a handful of epochs and often see pretty significant improvements in generalization. And this is something we've observed over a wide range of applications. So image classification, as well as language modeling, as well as using fully connected nets for regression, as well as semi-supervised learning, etc. And so this was the sort of first step towards trying to leverage that geometric information in order, that it's already captured by the SGD training in order to find a better solution. The next step is to see whether we could actually construct an approximate posterior. So stochastic weight averaging essentially takes the first moment of those iterates. We can also take an approximation to the second moment and get a low rank plus diagonal representation of a Gaussian approximate posterior covariance matrix. So this whole procedure is referred to as SWAG, SWA Gaussian, and the associated paper is called A Simple Baseline for Bayesian Uncertainty in Deep Learning, and we call it a simple baseline because it truly is very simple. The whole procedure is expressed on this single slide here. We just run SGD with this learning rate schedule. Once we've decayed to the high constant learning rate, we take an average of the different weights that we're traversing in this single SGD chain, and then we compute this low rank plus diagonal approximation to a covariance matrix just given in the equation in the bottom right here. And then we use our Gaussian approximate posterior with those moments in order to sample and compute our approximate Bayesian model average. So there's some theory suggesting that SGD with certain learning rate schedules will asymptotically be sampling from a Gaussian distribution and that its moments will be an accurate description of the geometry of the loss surface. But that theory makes assumptions which don't entirely hold in deep learning. So as a sanity check, we looked at what was happening in particular directions that might be especially relevant. So we looked at the principal components, for instance, of these SGD iterates and visualized the loss landscape in the basis given by these principal components and showed that this SWAG procedure was actually doing a pretty good job of capturing the loss surface or the posterior in those directions. So this visualization here is actually akin to the fancy visualizations we had earlier, where each point basically represents a very high dimensional weight vector, which is corresponding to some affine composition of 3 different weight vectors. And the color here corresponds to the value of the loss. evaluated at those points. So we applied this SWAG procedure to a number of different problems, including calibration problems. So when we normally train a convolutional neural network, we often get a miscalibrated solution, meaning that if we look at, for example, the highest softmax output and interpret that as a probability, the probability that the input actually has that associated class label is often much lower. So if the highest output is 0.9, rather than there being a 90% chance that we have that class label, there's more like a 70% chance that we have that class label. So neural nets are very often overconfident. And we can actually understand this fundamentally from a Bayesian perspective. When we do classical training, we're betting everything on a single setting of parameters. But in fact, we don't really have enough information to say that we believe that those are the right parameters with 100% certainties. We're actually ignoring that epistemic uncertainty, that model uncertainty, in which case we would, of course, expect to be overconfident. So when we do a Bayesian model average and we represent this epistemic uncertainty, we should help calibrate these models, which of course is crucial in decision making. If we're looking at an X-ray or something, we don't just want a black box prediction about whether there's a pathology or not. We want probabilities that we can trust to some extent in order to make a decision about what to do about that prediction. So in each of these figures here, on the vertical axis, we have confidence minus accuracy, where confidence is the highest softmax output that we have from our convolutional neural net, and accuracy is the accuracy of using the associated class label to make predictions. On the horizontal axis, we have different confidences. So we've just binned these confidences together. A perfectly calibrated model would just be represented by a horizontal line at 0 here. An overconfident model would be above that line, and an underconfident model would be below that line. So in green, we have regular SGD training. We also have a variety of other procedures, like a dropout-like procedure. In yellow, we have a temperature scaling procedure, which is a popular non-Bayesian approach to calibration. In brown, we have a Laplace approximation in pink. And we have the SWAG procedure in blue, as well as a diagonal variant in orange. And we see that SWAG does generally provide the best calibration of these choices. We also see that it's very scalable. So in the bottom row here, we have huge neural networks, a DenseNet 161 on big data sets like ImageNet, and we're getting results as quickly as we would get using standard training, at least at train time. We can see that the models are still a bit overconfident, but there's a significant improvement by doing this approximate Bayesian model averaging. In the top right panel, we have a somewhat different setting where we're actually doing transfer learning or covariate shift, domain adaptation. And we're training on CFAR10, but then testing on this different data set, STL10. Now, this problem setting is particularly interesting from a Bayesian perspective because many of the alternative approaches to calibration, like temperature scaling, require doing validation on a set that's representative of the target distribution that we're going to be testing on. Whereas the Bayesian model average is essentially just trying to represent epistemic uncertainty. And so it doesn't, in principle, require this to the same extent. And indeed, we see that although all of the methods are overconfident on this covariate shift problem, they're all above this horizontal line at 0, SWAG is quite significantly better than temperature scaling in brown, as well as many of the other alternatives. I would add also as a note that we kind of understand why Bayesian model averaging helps with calibration. We don't fully understand why many of the other non-Bayesian heuristics that are popular, like temperature scaling, really work. In a sense, it's actually surprising that temperature scaling can work as well as it does on problems like CFAR and ImageNet. The basic idea is just it's a special case of plot scaling. You just rescale all of your logits by a single hyperparameter, the same hyperparameter for all of them, and then you tune that with cross-validation. We don't really know, why that helps. It's almost surprising, and so in a sense, that's also a little bit of a red flag. It means that if we try to deploy this procedure on an entirely new problem, we have no idea whether it's really going to work or any assurance that it might work. Whereas with the Bayesian model averaging, we at least understand why it could help with calibration. So we can also quite naturally visualize epistemic uncertainty representation in regression problems. So here we have 3 clusters of data points, and we're visualizing the predictive distribution. And we see that with the SWAG procedure, as we move away from our observations, the spread of the predictive distribution increases. And we would expect this because as we move away, there are many more kind of consistent solutions with our observations. And so that's really a manifestation of epistemic uncertainty representation, representing model uncertainty. We can see in the right panel here, where we use a standard variational approach, that the predictive distribution is fairly homogeneous. So although the mean fit might be reasonable, the representation of epistemic uncertainty could be greatly improved. We see that everything looks a bit homogeneous. So this is actually quite a good test of epistemic uncertainty representation. There's a similar property in classification. If you're averaging over many different solutions, then you'll find that your decision boundaries sort of bend toward the clusters of data, such that when you move far away from the data, you have more uncertainty. So in summary, this SWAG procedure is a simple and scalable approach for Bayesian deep learning. It works simply by fitting SGD iterates with a low rank plus diagonal Gaussian approximate posterior, and it essentially recycles geometric information that we would get already through SGD training, and it can improve predictions and uncertainty at the ImageNet scale with large modern neural networks. So when I was introducing this approach, in order to justify the approximation, I said that we could visualize the loss surface in the space given by the principal components of the SGD iterates. And so this leads to the question of whether we could actually just directly do Bayesian marginalization in this space. One of the biggest challenges towards realizing a Bayesian approach in deep learning is the dimensionality of that integral that we want to compute. We have like a 10+ million dimensional integral. And while we can construct better approximations than we might get through classical training, there's still huge room for improvement, and this dimensionality is a challenge. So the contention in this work on subspace inference is that although the neural network might be represented by a high dimensional parameterization, a lot of variability in the functions given by the neural net could actually be captured in a very low dimensional subspace. And so the idea here is to first construct a subspace of a network associated with a high dimensional parameter space, and then perform inference directly in the subspace. And there are a variety of choices we can use once we have that subspace. If we're in a low dimensional subspace, we could often even just use very classical MCMC algorithms, which are quite good at exploring low dimensional parameter spaces. So we found, in fact, that we could approximate the posterior even of a wide residual net with 36 million parameters in a 5-dimensional subspace and achieve very good performance, much better performance than if we were just to do classical training. And so in particular, we define a subspace essentially as an offset W hat plus a linear projection P of a low dimensional vector Z. And so if we had a 5-dimensional subspace, Z would just be a 5x1 column vector. P would be a D by 5 dimensional projection. And W would be our D by 1 offset vector. So we typically chose W hat by using the stochastic weight average, the SWA solution. Once we have that subspace, we can perform inference directly in Z space. And then we can use the Zs that we get to basically, in conjunction with this equation here for the likelihood, to get Ws that we then use in our Bayesian model average. And so let's return to this mode connecting subspace. In the left panel here, we have the functions that are associated with parameters in the right panel in the mode connecting subspace. So you can see as we move along in this subspace, we actually get quite a lot of functional variability. And if I were to ask you, which of these functions would you use, this purple function or that purple function, you probably would have a hard time saying. And so with the Bayesian approach, we're just integrating over all of these different solutions to get our predictive distribution that's given in blue, which we can also see does seem to be intuitively providing a good representation of epistemic uncertainty. We can see the predictive distribution very naturally spread as we move away from the data, where we would expect a variety of different solutions to be quite consistent with our observations, and then contract as we move towards the observations. So this is a subspace given by that mode connecting path. Here we look at two additional subspaces. We can get a subspace just through a random projection. So that's what we would get if we were to randomly sample the parameters of that projection matrix P from a Gaussian distribution. We can see that it provides a reasonable mean fit to the observations here, but it doesn't do a great job of capturing epistemic uncertainty. The predictive distribution is very homogeneous. Here we consider a PCA subspace, so that's really what motivated this approach to begin with. Precisely to create that subspace, we would have a matrix which has as its columns the different iterates, the different weights that we're passing through using SGD with this modified learning rate schedule, this high constant learning rate, minus their average. So we would have, for example, W1 minus W bar, where W bar is the average of all of the different weights that we're traversing. Then W2 minus W bar is the next column, and so on. And then we would take a partial SVD of this matrix, and that would give us our P matrix, our projection matrix. So this is the subspace spanned by the top principal components of this set of iterates that we're traversing with this modified learning rate schedule. And the reason this is an interesting subspace is because PCA tries to capture variability in parameter space. And if variability in parameter space is a decent proxy for variability in function space, then we should be able to benefit by using this type of subspace in performing our Bayesian model average. Remember, we're trying to create a low-dimensional subspace that has as much variability in function space as possible, while also containing a variety of good solutions, not just a variety of solutions. And so this procedure actually costs about the same as classical training. You just need to do this one SVD. It's a very low rank principal component representation. So we might just take a 5-dimensional representation. So this is a one-time computation that doesn't take more than a minute on a laptop. And then once we've done it, we just do inference in this low-dimensional subspace, which is very fast. And so the whole procedure at train time is about the same as just classical training. And then here we have, again, the mode connecting subspace, which is a form of multi-Bayesian marginalization, which we'll discuss a lot more in the next part. And so here we actually see this empirical realization of the idea that we mentioned at the beginning of the talk yesterday, that if we're performing Bayesian marginalization, we ought to see improvements in not just calibration and log likelihood, but also in the accuracy of our point predictions. So in going from SGD to a random subspace on CFAR 100 with a good residual network, we go from 78.5% accuracy to 80.2% accuracy, which is a pretty big leap, especially if we're not paying more at train time. And then if we use the PCA subspace, we go up to 80.54%. If we use the curve subspace, we go up to 81.3%. And so these are very non-trivial gains in accuracy, especially considering that we're just recycling geometric information in the SGD trajectory to do this scalable Bayesian model average. The Laplace approximation has been a historically important approach for approximate Bayesian inference with neural nets. A lot of the early work that was being done by David Mackay deployed a Laplace approximation, which chooses a Gaussian approximate posterior through a second-order Taylor expansion around the log unnormalized true posterior. So the procedure is very simple. We start by saying, let's use a Gaussian approximation to our posterior over our parameters W, and then we will center that at the map setting of parameters. So this is just what we get if we do regular training, essentially. And then we'll compute the Hessian of the log posterior at that point, and then use that to form the covariance matrix or the precision matrix of our Gaussian approximate posterior. Now, of course, if we're working in a very high dimensional space, that Hessian is going to be impossible to use or store. And so typically, rather than use the full Hessian, one uses just a diagonal Hessian, or recently a Kronecker factorization of the Hessian, such that we represent that covariance matrix as a Kronecker product of much smaller matrices, which makes it more computationally tractable, but also more expressive than if we were to use a diagonal approximation. Once we have that Gaussian approximate posterior, we typically sample from it to form our approximate Bayesian model average. So this approach is compelling in that it's fairly simple. Its drawback is that it is very locally defined. And so it's entirely defined by the curvature, for instance, of the loss surface at the map solution. And so if there's a little kink or something like that, we could imagine pathologies where we get a very, very overly compact representation of that posterior. This is in contrast to some other approaches that use Gaussian approximate posteriors, including SWAG, where you have, for example, this high constant learning rate that's just bouncing around within some general basin of attraction. It won't be as locally defined, for example, by little kinks in the loss surface. It'll provide somewhat more of a global approximation. MC dropout is also another historically important approach. The idea is to run dropouts at train and test, basically randomly dropping out hidden units, each with probability R for each input. In regression, we can have the network output both a mean and a variance, and we can train those just through maximizing, for example, our Gaussian likelihood. And then once we have this ensemble of models created through this dropout procedure, we can just do an average, and this will give us some representation of epistemic uncertainty. I would note that unlike standard Bayesian model averages, this model average wouldn't collapse. So in the first part of the tutorial, we had this note about how Bayesian model averaging in general is not model combination, in the sense that the assumption is that one of these models is correct, and we're just averaging multiple models due to a statistical inability to distinguish between these models given limited information. As we get more and more data, eventually we'll see a collapse onto the maximum likelihood solution. That's not something we'll see here. So this is more like a different type of ensemble that's being formed in the end, although it is a way of representing epistemic uncertainty. So an interesting future direction here could be, for example, to do inference over things like the dropout rate, such that you would actually observe some kind of collapse as you get more and more data. Another historically important approach is called Bayes by Backprop, where you essentially introduce typically a Gaussian approximate posterior, and then you learn the parameters of that posterior so as to minimize the KL divergence between the approximate posterior and the true posterior. You can manipulate the KL divergence to get what's called an evidence lower bound, or an elbow, which can be optimized with SGD and backpropagation. Stochastic MCMC is a very up-and-coming approach to inference with large Bayesian neural networks. I think it's very exciting because algorithmically, as we can see here in this equation, it essentially is SGD plus a special type of noise. And this means that wherever we're using SGD or Atom or some other optimization procedure, we can also use stochastic MCMC and often see performance gains for doing so. However, as I mentioned also, unlike with optimization, where ultimately, in principle, we're just trying to find a low-loss solution, with sampling and with Bayesian inference, we really want to explore the loss surface. And so this means that the learning rates are going to be even more important in stochastic MCMC than they will for SGD, for instance. And we found recently that a cyclical schedule is actually quite effective in conjunction with stochastic MCMC. The motivation here is that we have high learning rates that encourage exploration, and then we have sort of a decreasing learning rate, which allows you to sample within a basin or within a local region, and then you jump up the learning rate again to encourage exploration, etc. And so this really improves performance and makes stochastic MCMC a very compelling practical alternative to classical training. So here, rather than an approach to inference, we have an example of a Bayesian method in deep learning called the Bayesian GAN, where we're actually trying to put distributions over a deep generative model. So the idea here is we have a discriminator and a generator, as usual with a GAN, except we also now have distributions over parameters of the discriminator and generator, which means that we'll actually induce distributions a priori and in our posterior over discriminators and generators. And inference within this model was actually done with stochastic MCMC, stochastic gradient Hamiltonian Monte Carlo. And what we see in this picture here are 5 different 6 different samples from our posterior over generators in the top row. And then with each of those generators, we see samples of different images, in this case for the MNIST data set. And interestingly, the different samples in each column here in the top row have qualitatively different properties. And so, for example, one panel might be capturing particular writing styles, another particular writing utensils, etc. And so this is basically a way of naturally representing different generative hypotheses for the data. It's not a way of trying to sample high fidelity images. So if that is our goal, then maybe we actually do want to bet everything on the most likely hypothesis, which would be like taking the mode, for example, in this conceptualization of a posterior over generator parameters given data. And that's what methods like DC GAN do, as we show in this paper called the Bayesian GAN. However, we see that if we retrain a DC GAN model 6 times, in the second row here, the samples we get from each of these DC GANs are fairly homogeneous. So we aren't capturing this different types of structure, which can be very important if you then want to use these generative models as part of another procedure, for instance, like semi-supervised learning, which I think is actually a nice quantifiable way to leverage a lot of the exciting progress that we've seen in deep generative modeling over the years. Creating pretty pictures is fun, but I think if we have a good generative representation for our data, then we can leverage that for all sorts of exciting prediction problems. And I think this is something we'll start to see increasingly in the future. And I think we'll also start to see Bayesian treatments of deep generative models more and more in the future. I think we haven't seen it too much yet, partly because the community has been focused on the significant but easier challenge of trying to marginalize distributions over parameters in simple supervised settings. So if we have a good generative procedure, we can also use it, for instance, in Bayes classifiers, where we have class conditional density, which is given by our deep generative model, and then we invert it using Bayes' rule to get a decision rule, which is also nice because we're focusing our modeling efforts on an object of interest, which is a bit more interpretable and richer in structure than just looking at class labels. Finally, deep ensembles has been a very popular approach to epistemic uncertainty representation in deep learning and has achieved very good practical results. The basic idea is to specify a neural architecture and then retrain that architecture multiple times to find different SGD solutions. So we get a set of weights, W1 to Wj, associated with retraining this model j times. In regression, again, each model can be specified to output a mean mu and a variance sigma squared. And then we take an equal average of the corresponding models that we get to form our deep ensemble. So I'm including this method in a section about practical methods for Bayesian deep learning, which might make you scratch your head a little bit initially, because indeed, deep ensembles have actually been presented in many papers as if they're an alternative to Bayesian deep learning, a non-Bayesian approach to getting uncertainty in deep learning. Whereas in this presentation, I'll actually argue that they're quite Bayesian, and in fact, more Bayesian than many of the approaches that are being referred to as Bayesian in these papers. And we'll unpack this a lot in the next part, but the basic intuition is that if we're actually fundamentally trying to compute this integral corresponding to our Bayesian model average, then deep ensembles is a very good heuristic for trying to do that, conditioned on finite amounts of computation. Very simply, if I were to say, we need to get the best possible estimate of this integral, and we're only allowed to query our parameter space, for instance, at 5 different locations, I doubt very many people would say, I would choose 5 exact samples from the exact posterior and do a simple Monte Carlo approximation. Because we know that's going to be very wasteful. What if the functions are pretty homogeneous wherever we happen to sample, for instance? And so I would argue that we really need to move away from this simple Monte Carlo approach to Bayesian model averaging, especially in deep learning, where we are quite constrained in the number of models we want to consider in our ensemble corresponding to the Bayesian model average. And deep ensembles basically says, well, let's choose these different basins of attraction, and as it happens, there's actually a lot of functional variability in the conditional predictive distribution at those different locations. And so each of those models will make a pretty good contribution to that integral we're trying to compute. Whereas if we're just sampling, for example, within a single basin approximation, then many of those samples won't provide the same level of functional heterogeneity, and therefore won't contribute as much to approximating this integral that we really ultimately want to compute. Okay, so that's the end of part 3, and in about 15 minutes, we'll start on to part 4. All right, so welcome back to the final parts. So this will just be about 30 minutes, shorter than some of the other parts, and then we'll do the fireside chat where we'll take questions and discuss my experience as a student and a few other things. Okay, so in this last part, we'll really be thinking about model construction and generalization. And in the interest of time, I won't talk too much about some of the material that we considered at the beginning of the first part, where we were looking at this plot of all possible data sets. But very briefly, we can conceptualize all data sets on one axis of this figure and the marginal likelihood or Bayesian evidence on the vertical axis as expressed by this integral. The evidence is the probability that we would generate a data set if we were to randomly sample from the parameters of our model. And very crucially, I would argue that the generalization properties of a probabilistic approach depend largely on 2 key features: the support, which types of data sets we're able to represent a priori, and inductive biases, which is the distribution of that support, which solutions are a priori likely. And so we could have a simple model like that linear model with the distribution over the slope and intercept that can't generate many data sets, but the data sets it can generate, it gives a lot of mass because this is a normalizable probability density. We could imagine some other model like a huge MLP, a vague distribution of parameters, being able to generate lots of data sets, but not many with much more probability than others. And we could finally consider a convnet, which has nice properties like translation equivariance, which give it really good inductive biases towards certain types of data sets, like structured image data sets, such that there'll be quite a lot of mass for those data sets, but still quite a lot of flexibility. And so such models will cast a wide net such that we can contain something like a ground truth description of reality, but can also efficiently contract around that good description because of the inductive biases. The simple models become quickly constrained by the data, but they're sort of erroneously constrained and they contract around a bad solution. And these, I would say, maybe complex models where complexity is defined as kind of thinly distributing our support over lots of different data sets, might contain a setting of parameters which is a good description of reality, but it's very hard for the model to contract around that setting of parameters because of those inductive biases. All right, so at the very end of the last part, I started to describe how deep ensembles could be perceived as a Bayesian procedure. Here we've got the Bayesian model average that we want to compute again. And in these 3 panels here, we have first the posterior distribution, just a conceptualization. Then we have the conditional predictive distribution, y given w. And then here we have something quite different, the distance between the true posterior and the approximate posterior that we get if we query our conditional predictive distribution in weight space at a given location, assuming that we've already queried it at this mode here, given in dark green. And so here we're kind of viewing the whole integration problem almost as like an active learning problem. It's like, given that I've queried this point, where should I go next in order to get a good approximation to this integral? And since there's quite a lot of variability in the conditional predictive distribution between these different basins, it's quite advantageous just to jump to another basin, which is something that we get through deep ensembles. We could generalize this procedure further to also marginalize within basins. And so multi-swag is an example of an approach that does that, where we basically have multiple independent swag models. And so we can try to get, basically both multi-basin marginalization and within basin marginalization. Okay, so let's study this a little bit further. In the top left, we have close to an exact predictive distribution, which has been formed by running 200 independent HMC chains for a very long time. In the top right, we have the deep ensembles predictive distribution. And in the bottom left, we have the predictive distribution that we get from a single basin variational approximation. Now, we can see just visually that the variational approach isn't doing a great job of capturing epistemic uncertainty. The predictive distribution doesn't spread that much between the different data clusters. We can also look at, for instance, the Wasserstein divergence between the predictive distribution in each case as a function of the number of samples that we're taking, where for deep ensembles, the number of samples is the number of independently trained models. And see that basically the deep ensembles approach provides a predictive distribution which converges much more quickly to the true Bayesian model average as we take more samples than just taking more samples in the single basin variational procedure. In fact, taking more samples within this single basin here doesn't seem to really be improving the approximation to the unconditional predictive distribution, the predictive distribution not conditioned on our parameters W, which is also an interesting observation. So the point here is not really to do, say, like a like-for-like comparison and be like, oh, deep ensembles is better than VI. If we wanted to do that, then we should probably just ensemble a bunch of independently trained VI solutions. And I would actually expect that to work slightly better than deep ensembles. The point here is to say that multi-basin integration and representation is going to be very important for trying to accurately represent our Bayesian model average. And so in this sense, deep ensembles can be giving us something more Bayesian than what we would get through a single basin Bayesian approximation. Okay, so multi-swag essentially just says, let's use a mixture of Gaussians posterior formed from multiple independent swag solutions. And we can compare that to deep ensembles on a bunch of different data sets. Here we're considering corrupted CFAR data sets, so that you may have heard of the CFAR10C data set and so on. There are a variety of different types of corruptions that are considered in our paper, Bayesian Deep Learning in a Probabilistic Perspective of Generalization. And there are a couple key takeaways in this empirical study. One is that when we have a small number of independently trained models, say roughly 2 or 3, there's a pretty big gap between multi-swag and deep ensembles, multi-swag in green, deep ensembles in blue. Multi-swag also provides significantly better performance when we have a large number, when we have a large amount of corruption. So we can see that basically kind of moving from left to right and then from row to row. As the corruption increases, we see the gap increases. And this makes sense. I mean, the Bayesian models, in a sense, are trying to marginalize over uncertainty, and that will be more valuable when we have more uncertainty. And if there's more data corruption, we'll have more uncertainty. This purple curve is also something that's kind of in between the different approaches. So it's multi-SWA, which is like what you would get if you were to ensemble multiple SWA solutions rather than multiple SGD solutions. And the reason this might be compelling is at test time. So although multi-swag and deep ensembles are requiring the same training time, if you're carrying around a big ensemble, which you might get through something like multi-swag or by taking lots of samples within each basin, this is going to cost you a test time. And so by basically representing each of those ensembles with a single model, which is kind of what the SWA approximation is trying to do, and in fact, in the original SWA paper, it was partly motivated by approximating an ensemble with a single model, you also save at test time. So the pink curve is kind of a compromise that is practically useful at test time. And there are many other experiments in the paper, especially in the appendix. So double descent is recently been a very active area of research. This finding sparked a lot of interest a couple years ago. And basically, it shows that there are essentially 2 generalization regimes for deep neural nets, but also many other models, where in the first regime, as we increase model capacity, performance starts to improve up to a point as we're just able to discover more interesting structure in the data with those more flexible models. And then as we continue to increase the capacity, we start to overfit and performance gets worse. So that's kind of the picture that we're all familiar with historically. Interestingly, however, as we continue to increase the capacity of the model, the performance again starts to improve. And so that other regime is sometimes referred to as the modern interpolating regime. And in this regime, we typically also have 0 training loss, as we can see with the dashed black curve here. So given everything I've said in this presentation today and yesterday, especially yesterday, I'd like you to consider whether we might expect a Bayesian approach to deep learning to also experience double descent. And so the question is, do you think a Bayesian deep learning model should exhibit double descent? 1, yes, 2, no. Let's just take a quick poll. Awesome, seeing lots of 2s. Great, that makes me very happy. The idea basically goes back to that very first question we had in yesterday's talk. Would we use the cubic polynomial, for instance, or the 10,000th order polynomial? I said, use the 10,000th order polynomial, embrace flexibility, don't worry about parameter counting. And in fact, if we have a reasonable prior and exhaustive marginalization, then we would predict that double descent wouldn't exist if we were to follow a Bayesian approach. We should monotonically improve in performance with increases in flexibility because we're able to capture additional subtleties in the real world, which will be important for making the best possible predictions. Okay. This is what we get. So here we have CFAR 100 with 20% label corruption. We see a clear double descent curve. We look at swag. We see less of a double descent trend, but it's still present. Multi-swag, we see no double descent whatsoever. Performance clearly improves monotonically with increases in flexibility. It's also quite interesting to note the pretty significant gap in accuracy between these three approaches, SGD, swag, and multi-swag. So SGD at a width of 20 here for the ResNet gives us about 45% error just over. Swag gives us 40%, so that's also a big jump, exactly the same training time for those approaches. And then multi-swag gives us another huge jump down to below 30% error. We have to pay more in training time, but this is still notable and reinforces the idea that if we're doing more exhaustive Bayesian marginalization, then we ought to also significantly improve in accuracy. Right, so I said reasonable priors and exhaustive marginalization. So let's talk a little bit about priors. So quite often, one just uses a fairly simple parameter prior in Bayesian deep learning. Like we might say we have a Gaussian prior over the parameters, each with variance alpha squared. And this combines with a neural network architecture to induce a distribution over functions. So in the second part of the talk yesterday, we really emphasized the function-based perspective. We do not care about the prior over parameters in isolation. All we care about is how that combines with the functional form of the model to induce a prior over functions. And in the case of Bayesian deep learning, the neural architecture itself prescribes many of the properties that we would want in a distribution over functions. For instance, the architecture is hierarchical, and we want to capture hierarchical structure in a lot of modeling problems. Convolutional neural nets capture properties like translation equivariance, the idea if we translate an image, we probably want our class labels to be invariant. And so, in a sense, if we were thinking about how can we create better priors for Bayesian neural nets, it would almost be exactly the same question as how can we create better architectures for Bayesian neural nets? The architecture itself is a huge assumption. And so from that perspective, even if we're not kind of formally being Bayesian, we are still kind of being a bit Bayesian when we're thinking about architecture design, even if we're not thinking about distributions over parameters. We have to make assumptions in order to make good inferences. And we shouldn't hide from them. We should just be transparent about them. And in fact, there's a lot of empirical support to suggest that a pretty kind of generic distribution over parameters, like this Gaussian distribution combined with an architecture, does provide a pretty reasonable distribution over functions, as I think we would expect from the architecture. So there's this result in the deep image prior paper that randomly initialized CNNs without training provide excellent performance for image denoising, super resolution, and inpainting. And so this means that a sample function from this induced distribution over functions captures low-level image statistics before any training. In the Rethinking Generalization paper, they showed that pre-processing CFAR 10 with a randomly initialized, untrained convolutional neural net dramatically improves the test performance of a Gaussian kernel on pixels from 54% accuracy to 71% accuracy, with only an additional 2% from L2 regularization, which is like tuning this alpha parameter. So all this is saying is like random samples from this distribution over functions that we get through this generic distribution over parameters are actually pretty reasonable in a lot of ways. They're doing something quite interesting. They're allocating mass to good solutions in general. Now, quite often in Bayesian methods for deep learning in particular, it's common to do something called tempering, where we raise the likelihood to a power 1 over t. T is less than 1. We have what are called cold posteriors, which favor the likelihood a bit more than the prior. T equals 1 is the standard Bayesian posterior, and t is greater than 1 might be a warm posterior, where the prior is having a stronger effect. It's kind of slows down posterior collapse. And so it's been noticed that quite often, by making t less than 1, we can achieve better performance. And sometimes when t equals 1, there's even worse performance than classical training. And there have been a number of suggestions for why that's the case. In this cold posteriors paper that was at ICML, they suggested that the result is due to prior misspecification, and they show that sample functions from this induced distribution over function seems to assign one label to most of the classes on CFAR10. So we take one sample function, apply it to all of CFAR10, and it's saying most of this data set is label 6, for instance. And then we do that again, and it says most of this data set is label 9, which seems kind of dramatic. But in fact, there's a lot of subtlety here that's worth considering. So here we've reproduced those results corresponding to different settings of that alpha parameter, basically the variance scale of our distribution over our parameters. So if we make alpha root 10, then we kind of get that same result in the far right column, top 2 rows. However, we should note that when we actually combine all these prior samples together to make predictions, which of course is what we need to do when we form our Bayesian model average, we see a pretty uniform vote across classes. So, that's fine. And not too worrisome in the end when we're making predictions. We also see that as we scale alpha, the different sample prior functions start having a more and more uniform distribution over the different classes. And so, of course, alpha is something that we would want to tune. It probably is a bit misspecified if we make alpha equals root 10. But this is something we can tune through cross-validation, or we can just set it to what we would use for L2 regularization. So in a sense, choosing a bad alpha is a bit like saying, well, let's just train our neural net with L2 regularization and just choose some kind of random sort of like amount of L2 regularization, which of course is not something we would do in practice. And so when we see that it's actually pretty robust to alpha, and the predicted distribution throughout is giving us essentially a uniform vote. We can also see the effect of data on the posterior when we have a misspecified prior, which is quite interesting in itself. And so if we set our alpha equals root 10, we do get this artifact where the different sample functions are assigning most probability to one class. But if we observe even 10 data points, we see that the posterior updates very quickly to assign a more uniform distribution. Then 100, it's basically even across the classes, 1,000, and so on. And so what this is saying is, although misspecifying alpha does result in some amount of prior misspecification, it's kind of a pretty soft prior bias that we're talking about that will be very quickly modulated by data. And we can also understand this from the Gaussian process perspective. It's sort of like saying, let's multiply our kernel by a big value or misspecify our length scale. So if we multiply our kernel by a big value, the amplitude will be very large. But if we observe data points that are constrained within a particular region, we'll see the posterior quickly contracts. And so this is the kind of misspecification which ultimately may not affect generalization that much. What will matter a lot more for generalization are properties like the induced correlation or covariance function we get in this distribution of our functions. So whether or not we use an RBF kernel with a sort of amplitude scale of 10 or 100, I would say in many cases doesn't really matter if once we've observed a reasonable amount of data. Whether we use a GP with an RBF kernel or a Mathieu kernel or a spectral mixture kernel or a deep kernel, that will really matter, almost no matter how much data we observe, practically speaking. And so it's important to look at these types of properties. And we see, in fact, that the induced covariance function does tend to have desirable properties a priori when we have a pretty generic distribution over parameters combined with a neural architecture. For instance, we see that images of the same class label are more correlated than images of different class labels. Visually similar appearing images tend to have higher correlations than different looking images. The magnitude of these correlations are controlled. We can see a bit through this alpha parameter. So a few thoughts on tempering. And this also speaks to, I think, Bayesian inference at large, not just Bayesian deep learning. It would be surprising if we found that the t equals 1 was the best setting of that hyperparameter. I mean, this is another parameter. It can take any value. We know what kind of effect it will have. It would be kind of amazing and magical for t equals 1 to be the best setting of that parameter with hindsight. And so this does seem like, it's something that we should tune. Our models are definitely misspecified. And I think having a t not equals 1 typically, although not always, is a recognition of misspecification. But that's just part of honestly following our beliefs in our modeling procedure. And I think at a high level, that's what Bayesian methods are all about. They're about trying to most honestly represent our beliefs. That includes trying to have a lot of flexibility, honestly acknowledging the fact that the world is a complicated place and we want to capture the nuances in that structure in order to achieve good performance. But I would argue it also means honestly reflecting the belief that no matter how hard we try, and we should try hard to specify our prior nicely or our likelihood, we're going to have some amount of misspecification. And so we should account for that. And so that would be in line with procedures that people refer to as generalized Bayesian inference or safe Bayes. And I think it's something that we should really embrace as a community. Also, while the prior will be misspecified, the result of assigning one class, as we've described, to most data in sample functions from the induced prior over functions is more of a soft prior bias, which doesn't hurt the predictive distribution. Once we do the Bayesian model average, is easily corrected by appropriately setting the prior parameter variance alpha squared and is quickly modulated by data. It's more important to think about things like the induced covariance functions. We see that the deep image prior and random network feature results also suggest that the prior is quite reasonable using these generic distributions over parameters. And in addition to not tuning alpha, the results in the cold posteriors paper could also have been exacerbated due to lack of multimodal marginalization. So we've been seeing a lot in this part how important it is to try to marginalize between different basins of attraction. And so that wasn't done in that paper, and I think could be quite important to the results. It's also interesting to note that even if we do entirely believe our prior and our likelihood, there are cases where cold posteriors could be helpful given a finite number of samples. And this point also harmonizes with the observation that we were making about how to best do a Bayesian model average under computational constraints. In the real world, we always have to deal with these types of constraints, and we have to reason about how we can come up with the best possible model under those constraints. And so from that perspective, for instance, deep ensembles is actually quite a compelling Bayesian heuristic. Similarly, we could imagine, for example, that we're trying to estimate the mean of a high-dimensional Gaussian distribution. So if we take samples from that distribution, what you'll find is that those samples have a norm that's almost exactly root D. And so this is a fun thing to try, at home. Look at a histogram of the norms of samples from a high D distribution. And so this means that if we actually have a temperature less than 1, given a finite number of samples, we'll do a better job of estimating that parameter. And so it's not always the case also that a t not equal to 1 is indicative of model misspecification. We have to take into account that our marginalization procedure is going to be suboptimal, and we're also running it for a finite amount of time. Now, there was another paper a few years ago called Understanding Deep Learning Requires Rethinking Generalization. And it showed that convolutional nets could fit CFAR with random labels. And of course, we know that these conv nets can also generalize on noise-free CFAR. And this was presented as in the face of everything that we know about generalization, because it showed that conv nets had the flexibility to massively overfit these problems, yet they were providing good generalization. From the perspective that we've been presenting throughout this talk, these results are entirely consistent. We would want a model to have a lot of flexibility to fit, whatever it observes. We also have to have good inductive biases. So generalization is not really a one-dimensional concept that's all about flexibility. We also have to care about the inductive biases. And in fact, we can reproduce these exact results using a Gaussian process model. And it's actually a beautiful demonstration of how we should not be treating flexibility even as a proxy for complexity. These are different things. GPs with RBF kernels are enormously flexible, but they're also not particularly complex and quite good at generalizing on problems with a small number of points. So in this top left panel here, we have sample functions from a GP with an RBF kernel, all with sort of similar statistical structure. In panel B, we have a fit using that prior to some data points in green, which provides a reasonable looking predictive distribution. In panel C, we additionally add a bunch of corrupted labels given in red, and we can see that the GP posterior is able to run through those perfectly with no training error. And this is because even though that red curve is not a likely draw from the prior. The model does not have inductive biases aligned towards that type of solution. We would have to sit there drawing functions in the far left panel for a very, very, very long time to see anything like that red curve. It does contain that type of solution in its support. And so if there's a strong likelihood signal saying you can't use noise to fit this data, then the model is flexible enough to capture that type of solution and give zero training error. And we can actually quantify precisely how much a model wants to fit a particular data set with the marginal likelihood, the probability that we would generate that data set under the prior. And so we can evaluate the approximate marginal likelihood for a GP on corrupted CFAR and show that it actually shoots down significantly as we increase the number of corrupted labels. And we also showed in this paper that we could actually reproduce these results and fit noisy CFAR with 100% training accuracy using a GP and still get reasonable generalization on the noise-free problem. We can similarly do this with Bayesian neural nets. So we can compute an approximate marginal likelihood and show that it decreases as we increase the number of corrupted labels. So we could imagine noisy CFAR in that diagram we've been considering where all possible data sets are conceptualized on the horizontal axis. Noisy CFAR is somewhere on that axis, and Bayesian neural networks have support for that data set, but just not very much support. And that's quantified by the marginal likelihood. And so the model can fit that type of data, but it doesn't want to. And that's because it has reasonable inductive biases. And that essentially resolves this question that was posed by this very impactful paper on rethinking generalization that won best paper at ICLR 2017 and has since had thousands of citations. And there are other ways to resolve this as well. So there have been a number of works sort of considering that result and explaining it in a variety of different contexts. So in terms of developing new priors for Bayesian neural nets, I think this is a promising research direction, but we should be careful because we don't necessarily want to be contriving priors over parameters to induce distributions over functions that resemble familiar models, such as GPs with RBF kernels. We could be throwing the baby out with the bathwater again. We already have GPs with RBF kernels. Neural nets are interesting precisely because they are different than other models. They have different inductive biases that are useful for generalization in a number of different application domains. I think that we can gain insights by thinking in function space, but in many cases, this will amount to architecture design, which will be useful regardless of whether we're following a Bayesian approach. PAC-Bayes has been an interesting way to provide explicit generalization error bounds for stochastic networks with, broadly speaking, posterior is Q, prior P. This expression in equation 11 describes the generalization bounds. Recently, in the last few years, non-vacuous bounds in some cases have been derived from exploiting flatness in Q, such that we might predict that we get no more than 20% generalization error on binary MNIST. This is a promising framework. It's satisfying in the sense that it allows us to say something explicit and quantitative about generalization performance, but it does tend not to be very prescriptive about model construction or informative for understanding why a model generalizes. So it's quite complementary to the perspectives that we've been describing in this talk. And this could be partly because although the bounds are in some cases non-vacuous, they're still fairly loose. For example, in binary MNIST, we know that we can get less than 1% error. And so what we do to improve the bounds won't necessarily improve generalization. Indeed, we can improve the bounds by a compact distribution P, having very few parameters. And this is partly because it's hard to have overlap, according to the KL divergence, with very large, very high dimensional distributions, Q and P. And often these bounds are derived by having very, very compact P. Whereas we've been arguing we want to have priors which have large support, which are diffuse in some sense. And many parameters. And when you look at many of the bounds that are derived, they are sort of counting parameters in many cases. Also, we've really seen the importance of multimodal marginalization throughout this part, how it can help resolve double descent and how it can provide much greater accuracy than what we would get through single basin marginalization, and how it can provide a much better estimate of our Bayesian model average, our unconditional predictive distribution. However, the generalization bounds in PAC-Bayes are not typically that affected by a multimodal posterior Q. You just get a log factor, so they're not changed that much. So I think it's an interesting kind of future research direction to see if we can derive generalization bounds that would be very influenced, for instance, by multimodal posteriors. So I think this is an exciting direction and quite complementary to the perspectives that we've been describing so far. We can also relate posterior contraption to a quantity called effective dimension of the Hessian. And so they're actually directly connected, and we described that in a paper called Rethinking Parameter Counting in Deep Models, Effective Dimensionality Revisited. And so to recap, the effective dimension of the Hessian is the sum of lambda I over lambda I plus alpha, where lambda I is the eigenvalue of the Hessian, and this is directly related to posterior contraction. And interestingly, you can show that if you have p parameters and n data points, the posterior, there'll be p minus n orthogonal directions where the posterior hasn't contracted. This quantity is also related to Occam's factors and minimum description length principles. And in a sense, the effective dimension can be viewed as the number of sharp directions. It's also different from other types of flatness measures that have been associated with generalization, like robustness of our loss under random perturbations. That will be really affected by, say, the single sharpest direction. And so the effective dimension is basically counting the number of sharp directions at our solution. And this will be the number of essentially determined parameters where the posterior is very contracted. So if you have two models with a similar value of training loss, we could view each of them as providing the same sort of level of compression of our training observations, and the one then with lower effective dimensionality will be providing, so each will provide the same fidelity of compression, but the one with lower effective dimensionality will be providing a greater compression, and so we would probably expect it to provide also greater generalization. And interestingly, this quantity can be used to quite effectively track properties like double descent. So we can see here where we have zero training loss, the effective dimension is tracking double descent quite closely. Here we're showing test loss, but it's also true for test error. And we can also use effective dimension to analyze width depth trade-offs. A lot of deep learning theory right now is considering what happens is we get very wide neural nets, for example, through neural tangent kernels and through these double descent-like figures where we're increasing the width of a model. But in a sense, depth is what has made deep learning interesting and provided it with good inductive biases for generalization. And we can see that above the green partition where we have zero training loss, where all our models are essentially providing lossless compressions of the data, the ones with the lowest effective dimensionality pretty reliably correspond to better generalization. And the yellow here shows level curves of models with a constant number of parameters, again emphasizing that parameter counting is not a great proxy for generalization. And though not everyone is saying that we should parameter count, I think parameter counting is quite prevalent in deep learning. So almost every deep learning theory talk opens with a discussion of over-parameterization, the fact that it might be surprising that we have these models with way more parameters than data points that are super capable of overfitting, yet are providing good generalization. And so we could argue that even the concept of over-parameterization is a form of parameter counting. And artifacts like double descent are also a consequence of parameter counting. Even though these models have more parameters at width of 60, they're actually providing simpler solutions. We can also understand from a non-Bayesian perspective why things like double descent could happen. So as we increase the dimensionality of our parameter space, flat regions will occupy a much greater volume in our loss surface. And so they'll be more easily discoverable by procedures like SGD. And these flat regions tend to provide simpler solutions for the data. And in fact, we did show that if we move in the directions given by the eigenvectors of the Hessian corresponding to the smallest eigenvalues, there was actually a lot of functional homogeneity. So we didn't see a lot of variation in function space as we move along those directions in parameter space. And so this actually provides an explanation for why we can compress so effectively in procedures like subspace inference, where we found that even in a 5-dimensional subspace, we could get a lot of functional heterogeneity. So in summary, we've been arguing throughout this talk that one of the key defining features of Bayesian methods is a posterior weighted model average, and that this will be especially important in deep learning, where we have diffuse posteriors that are capable of describing many complementary explanations to the data. And as a future direction, further understanding these loss landscapes will help us provide better posterior approximations and more effective approaches to estimating this BMA integral. To that end, we should also be careful about not viewing marginalization purely through the lens of simple Monte Carlo integration. If we're given a finite amount of computation, we don't necessarily want to just get high fidelity posterior samples. And I'm very excited to say that, practically speaking, Bayesian methods are often now providing better results than classical training in accuracy and uncertainty representation without a lot of significant overhead. And also, we should be very careful not to conflate flexibility and complexity. GPs, for example, are beautiful instances of models with a huge amount of flexibility, but not a lot of complexity in their inductive biases, good generalization on a small number of data points. By the same token, we should be careful not to treat parameter counting as a proxy for complexity. We saw yesterday that we could have models with even an infinite number of parameters and a lot of flexibility, but in many ways they aren't that complex. And we can take steps towards resolving mysterious results in deep learning by thinking about model construction and generalization from a probabilistic perspective. So that's everything. Thank you.